Hello students, good morning. Welcome to Heat and Mass Transfer live classes. This is Sekhar from Msigma Gokulam. Now I want to begin the very important subject in mechanical engineering, a mathematical subject considering consisting of derivations and its applications, a very practical subject. Because our day-to-day life, we observe these phenomenon of heat transfer very often. In fact, our body itself is a thermal system which is continuously losing heat to the surrounding atmosphere. Because from the day we came into this world till we leave from this world, your body keeps on losing heat from its skin to the surrounding, because your body is a heat generating machine. We continuously keep on losing the heat. That means our heat transfer itself we can experience, we can feel at every second of your life, because when life is there in a human body, its temperature will be 37 degrees Celsius, but of course the ambient temperature keeps changing, 15, 20, 25, 30, whatever may be the temperature. Because there is a temperature difference between the body and the surroundings, there is a heat transfer keeps on happening, sometimes by forced convection, sometimes by free convection, many times some part by radiation. So by convection or radiation or whatever it is, we are feeling, we are experiencing heat transfer from our human body to the surrounding atmospheric air due to the temperature difference. Basically, heat transfer, according to the second law of thermodynamics, heat transfer is a phenomenon which naturally occurs from high temperature to the low temperature. So I would like to mention that according to Clausius statement of second law of thermodynamics, heat always flows naturally or spontaneously from high temperature to the low temperature. So temperature difference is the driving potential behind any heat transfer phenomenon. Temperature difference is the driving potential behind any heat transfer phenomenon. But unlike in thermodynamics subject, in this subject we are always interested in calculating the rate of heat transfer per second, how much heat is being transferred from high temperature to the low temperature. So we are always interested in calculating rate of heat transfer, per second, how much heat is being transferred in joule per second or watts. We are always interested in calculating rate of heat transfer or the heat transfer rate in joule per second or watts. So this is the actually main essence of the subject. We are almost every problem of heat transfer, we finally arrive at the answer, which is the calculating the rate of heat transfer. Now let me teach you what are the ways, what are the modes of heat transfer. What are the three distinct modes of heat transfer? Okay, temperature, we know that temperature difference is the driving potential, because of that heat transfer happens. In what way it happens? Let me explain. Conduction, three distinct modes of heat transfer are there: conduction, convection and radiation. First let me explain the three distinct methods independently, then let us see what are the governing laws behind all these phenomena. Conduction. Supposing if you just take a metallic rod, for example, if you take a metal rod, one end of the metal rod is subjected to the high temperature, because maybe it is put on some fire it is kept, and other end is low temperature, maybe I am holding. But after some time I have to leave, I can't hold that low temperature anymore because I am sensing the high temperature there. I say that heat is conducting from the high temperature to the low temperature through metal rod. Heat is conducting through the metal, and how that conduction happens? The molecules in the vicinity of the high temperature, molecules of the rod, in the vicinity of the high temperature heat source called fire, because one end of the rod is kept on the fire. So those molecules of the rod which are in the vicinity or which are in the locality of the fire will pick up the heat energy, and those molecules become excited. Actually, unlike the fluids, in solids molecules don't have any kind of a freedom to move here and there. Try to understand. The entire matter consists of solids, liquids and gases. Liquids and gases put together are called as the fluids. So matter can be broadly divided into solids and fluids. The molecular freedom is much more in fluids, whereas in solids the molecules don't have any freedom to move here and there. They are hooked to their places. They are rigidly fastened to their places. They can't leave that place. But even though the molecules cannot leave their spaces, they have got another freedom called vibration. They can vibrate. When they get excited thermally, they may vibrate. Staying there only, they may get vibrated. So these molecules which are in the vicinity of the high temperature heat source, after receiving the energy, begin to vibrate like this and giving that vibrational energy to the next molecule. Next molecule begin to vibrate, and that in turn can give that energy to the next. So one molecule to another molecule, there is a molecular lattice vibrational energy transfer. Molecular lattice vibrational energy transfer. And this is only contributing to the around 20 or 25%. 20% of heat conduction happens like this. The remaining 80% conduction happen by free electron transfer. Molecules, metals, metal rods have the free electrons in the outermost orbits. Those free electrons receive the energy from the high temperature source, simply leave that atom and jumps to the next atom, giving the energy to the free electron present there. See, in the atoms of the solid metals are very good conductors of heat. The reason behind that is, metals are very good conductors of heat. The reason behind that is because there are plenty of free electrons available in the outermost orbits of the atoms contained in the molecules. Metals are very good conductors of heat. The prime reason is they do have free electrons or valence electrons in the outermost orbits. They receive the heat energy and jump to the next atom, giving that energy to the free electron present over there. That will receive the energy and jump to the next. So from molecule to molecule, there is a free electron transfer. So this is contributing to the 80% of the heat conduction. 20% is conducted by that molecular lattice vibration, and 80% is contributed to the free electron transfer. That is the reason why all metals are good conductors of electricity also. Take copper. Copper is a good conductor of heat and good conductor of electricity. The reason is the copper has plenty of free electrons in the outermost orbits. Copper, aluminum, steel, all metals, for that matter, all metals are good conductors of heat and as well as electricity. The prime reason is the presence of abundant number of free electrons or valence electrons which are present in the outermost orbits of the atom. So they carry the heat energy from atom to the atom, and thereby heat will be conducted. So 80% conduction by free electron transfer, 20% is contributed by molecular lattice vibration. So I write that conduction definition. Conduction is the mode of heat transfer which generally occurs in solids to temperature difference associated with molecular lattice vibrational energy transfer, and also by free electron transfer. All metals are good conductors of heat. You can say that by looking at that K of the silver, best known conductor is silver, 410 watt per meter Kelvin. K of this copper, around 385 watt per meter Kelvin. K of the aluminum, that is 200 watt per meter Kelvin. See, all are even the steels, steel, K of the steel. Steel is a better, good conductor. Iron is even better conductor. Generally, conductivity of the pure metal is greater than conductivity of its alloy. What is this conductivity? Conductivity is the ability of the material to allow the heat to get conducted easily. Supposing in the peak winter, if you touch the metal rod, in the peak winter, if you touch the metal rod, you feel chillness. If you touch any wooden bar, you don't feel that, because any metal bar has got a good conductivity. It can take the heat from you quickly. Therefore, heat conducts from your body through that metal rod quickly. So that is why we feel chillness. When you touch the any wooden bar, you don't feel like that, because wood is a very bad conductor of heat. Okay. Insulators have very low thermal conductivity. Okay. Example, glass wool, asbestos. Look at this thermal conductivity, that is 0.075. The K value is very low. Metals are having a very good conductivity value, and insulators have got very low value. Asbestos rope, like that. Refractory brick used in the furnaces. So the K value is low for all the insulators. Look at these metals, 400, 385, 200. K of the iron is around 45 or 50. Steel will be around 25 to 30. Okay. So, so we have seen the good kind. Whenever you want to arrest the heat transfer rate, whenever you want to reduce the heat transfer rate, you have to pack it with the insulator. Whenever you want to have the more heat transfer rate by conduction, put the good conductor. For example, fins are always made with very good thermal conductors. Always aluminum is the best fin material. Fins are made with a good thermal conductivity metals like aluminum. Aluminum is the best material. So whenever you want to reduce the heat transfer rate, we want to use the insulators like a thermocol. Naturally used insulators are thermocol, rice husk, the cover of the rice grain, okay, the rice husk, thermocol, and in fact and sawdust also, wooden sawdust, carpentry sawdust, that it can be used. So these are all the very bad conductors of the heat. Okay, gunny bags, sometimes the gunny bags also packed around the cold items to prevent the heat transfer rate. So these are all the day-to-day seen insulation methods as such. Okay, right. Now this is all about the conduct, but then the question comes to conduction in gases. Supposing if you want to talk about the conduction in gases, conduction in gases happens in a different way. Supposing if this is a high temperature plate, this is the low temperature plate, in between Now there is a high temperature plate, the gap may be around 1 mm, the gap may be is around 1 mm there, okay. It may be containing air. This air contains the continuously zigzagly moving molecules. Though the volume of the air is little, even though the volume of the air is little, it contains enormous number of molecules. So many number of molecules zigzagly moving, colliding among themselves, hitting among themselves, right? These molecules. So these high temperature, the molecules which are present in the high temperature plate, these are all the high temperature molecules. High temperature, they have because they are very close to the high temperature plate, high velocity molecules. These are all the low velocity, low temperature molecules. Because velocity of the molecule and temperature, they are interlinked. If the temperature of the molecule is more, velocity is more. That is how we define the kinetic theory of gases. From the kinetic theory, we say that if the temperature of the gas molecule is more, its kinetic energy or the velocity is also more. So these molecules are high. The molecules in this vicinity are having more velocities. The molecules in this vicinity are having a lesser velocities. These are all having the lesser velocities. But the molecules are not static, they keep moving zigzagly. So there is every possibility that the molecule coming from the high velocity domain may come into collide with the low velocity molecule and they exchange momentum. There is a molecular momentum transfer. Molecular momentum transfer, momentum exchange. That means high velocity molecule becomes slower, low velocity molecule becomes faster. That gains the momentum. High velocity molecule loses the momentum and low velocity molecule gains the momentum, therefore its velocity increases. That means beyond certain barrier, the high velocity molecules keep on moving and keep colliding with the low velocity molecules. Therefore, the low velocity molecules velocity kinetic energy also will increase after the collision. So as such, the temperature of these gases, these low velocity molecules will increase. Got it? When these high velocity molecules, when cross this boundary and collide with the low velocity molecules, they exchange momentum and transfer that momentum. That is how the velocities of the low temperature molecules will increase. As the velocity increases, because the RMS velocity is directly proportional to the square root of the temperature. When the velocity increases, this is called RMS velocity. When the velocity increases of the molecule, I say the temperature is also increasing. That is how we can say that heat is conducting, heat transfer by conduction. So conduction in gases occurs by molecular momentum transfer when high velocity, high temperature molecules, when high velocity, high temperature molecules collide with the low velocity, low temperature molecules. Okay. So that means conduction could happen even in gases also, but the mechanism of conduction in gases is different from that in the solids. In solids, by molecular vibration and free electron transfer. Here, molecules keep moving zigzagly in gases, and as the high velocity molecules collide with the low velocity molecules, there is an exchange of momentum, exchange of kinetic energy. As such, the conduction could happen by molecular momentum transfer during occurring during that molecular collision. So collisions are happening, momentum is exchanged, velocity changes are happening, and that is resulting in the conduction through the gas. Okay. So but as the temperature of the gas, that is the reason why as temperature of gas increases, its thermal conductivity also, its K value also increase. So, that point you have to remember. Right. Now, we have understood basically what. Now, onwards when you see the conduction, it is an internal phenomenon occurring through a solid body. Supposing this rod is there, I am keeping one end of the rod or a flame, the heat is conducting like this. So, what is happening within the solid body, what is happening, what is the heat transfer occurring within the solid body, we can perceive it as a conduction heat transfer. Then coming to the second mode, that is the convection heat transfer. Suppose that there is one hot plate over which a cold fluid is moving. So, this hot plate is a TW. There is sometimes after some time that hot plate will get cooled and attains equilibrium with the fluid there, fluid with some velocity. TW may be greater than T infinity. So, this mode of heat transfer is called as a convection. If it has got the velocity, it is called as a forced convection. If the same plate is losing heat to the surrounding air, still air, where the air is not having any velocity like this, it is called as a forced convection. Same plate, if it is losing heat to the still air, this is called as a free or natural convection. Okay. So, in convection is a mode of heat transfer occurring between a solid body and the surrounding fluid. TW is being greater than T infinity because there is a temperature difference. Okay, now the convection could be understood as that mode of heat transfer occurring between a solid body and the surrounding fluid, which may be flowing like in the case of the forced convection. If the flow is not there, but still air or still fluid is there, but heat transfer is happening, it is called as a free convection. So, but basically the convection should be understood as that mode of heat transfer occurring between a solid body and the surrounding fluid. Fluid could be water, fluid could be air, the fluid could be anything. A solid body losing or gaining heat with the surrounding fluid is a convection. We are all losing heat by convection. From my skin, what is happening to the surrounding air is by convection. If there is a fan is there, blower is there, it is a forced convection. If no fan, no blower, air is still stagnant, quiet air is there, it is a free convection or a natural convection. But how do in the natural convection heat transfer happens? First, let us see the forced convection. As the cold air flows over the plate, there is a picking up of the heat energy by the air from the plate. The thermal energy content, the enthalpy content of the fluid will increase. With that greater enthalpy content, simply the fluid moves away, takes away with that, goes away with that heat energy. It is supposing there is a plate, this is a plate. A fluid comes onto the plate, picks up the heat energy from the hot plate. As a result, the thermal energy content or enthalpy of the fluid will increase. With that thermal energy content, fluid goes away, takes away, gets away with that heat, and again fresh colder fluid comes, picks up the heat, that goes off. So, the process keeps on heating, keeps on happening until the plate arrives the same temperature, thermal equilibrium with the fluid. So, that is called as the forced convection if the fluid has velocity. In the free convection, what will happen is the air in the vicinity of the plate will pick up the heat. The temperature of the P by rho is RT. This is an ideal gas equation. So, as the temperature of the air increases for in the air in the vicinity of the plate, the density of the fluid will decrease. As the density of the fluid decreases, air becomes lighter. As the density decreases, air becomes lighter. Immediately, the buoyancy forces comes into picture because of the drop in density. The buoyancy forces comes into picture. They will provide the flow like this. The slowly slowly, steadily the air keeps moving up. Naturally air keeps moving up. Slowly, naturally it keeps moving up, and once it keeps moving up, there is a partial vacuum is created. To fill that vacuum, surrounding air keeps coming. So once the air gets displaced, in that above that plate there is a partial vacuum created. To fill that vacuum, the surrounding air slowly enters. That will pick up the heat, that becomes lighter, that moves up, that process keeps on happening. So fresh fluid keeps coming, after getting heated up, it becomes lighter and keeps moving up. So because why the lighter air is getting pushed up? Because of the buoyancy force. Hotter air is a lighter air. Lighter means low density air, and that gets pushed up by the colder and heavier air. Okay, so because of the buoyancy forces. So the driving forces in the free convection are buoyancy forces, whereas in the forced convection we have definite velocity. In a free convection there is no definite velocity, but motion is there. Motion is definitely there. We can see that with our naked eye also. Whether a forced convection or a free convection, there is always a macroscopic bulk motion of the fluid from one location to the another location, carrying the heat energy. I am writing the definition. Convection is the mode of heat transfer which generally occurs between a solid surface and the surrounding fluid. Due to temperature difference associated with macroscopic bulk motion of fluid transporting thermal energy or enthalpy. So the transporting thermal energy, fluid comes onto the plate, picks up the heat, and that will be taken off. Energy will be taken off, moved energy will be carried away by the fluid. Without velocity or with velocity, whatever it is. Without velocity, if the energy is carried off, motion is there, but no finite velocity, that is called as the free convection. If the motion of the fluid is provided by external agency, like fan or blower, like fan or pump, it is called forced convection heat transfer. On the other hand, if the flow of fluid occurs naturally, due to buoyancy forces, occurs naturally due to buoyancy forces arising out of density changes of fluid, it is called free convection or natural convection. Both mean the same, free convection or natural. Definitely the rate of heat transfer will be more in the forced convection. We are very pretty well aware. Suppose if you are given a hot plate, when you keep in front of the fan, it gets cooled faster as compared to the case where you keep it in still air. When you keep it in front of a fan or a blower, definitely, supposing if your hot body is there, you want to cool it, definitely you would like to put it in front of a blower or a fan, so that the forced convection cannot easily take away the heat from the body. So, same body, same fluid, the convection heat transfer rates are more in force than in free. So, this is the basically convection is the heat transfer or heat energy interaction or heat transfer phenomenon occurring between a solid body and the fluid. Okay. So, we are all losing heat by convection, sometimes forced, sometimes free. There is a third mode of heat transfer called radiation. In both conduction and convection, there is a medium involved. In the conduction, the molecules are vibrating, free electrons are jumping, whereas in convection, the fluid is coming onto the body and taking the heat and moving away from the body. So, matter is involved. This is the mode of heat transfer which does not require any matter. Conduction needs matter, convection needs matter, but not the radiation. How does it happen without matter involved? It happens like this. Supposing if you take a vacuum chamber, inside which if you keep two plates, one is high temperature plate and other is low temperature plate. Okay. After some time, if this is perfect vacuum you are maintaining, nothing is there here between the plates. Vacuum chamber, perfect vacuum chamber. And after some time, if you observe, both of them will arrive at the same temperature, thermal equilibrium. I say, yes, there is a radiation mode of heat transfer happened. Otherwise, how can they exchange the heat and how can they come to the thermal equilibrium? They have exchanged the heat without matter involved because they have reached the thermal equilibrium, same temperature after some time. How did they exchange the heat? By the radiation. How that radiation happens? It happens like this. According to the Prevost theory, all bodies at all temperatures emit thermal radiation. All bodies at all temperatures emit thermal radiation. Everything, you emit, I emit, everybody emits. Okay. But high temperature body emits more radiation because the rate of emission from the body mainly depends upon the temperature. There is a more emission happening. More emission. Why? Because the temperature of that plate is more. There is a lesser emission happening. Why lesser emission? Because the temperature of the plate is lesser. Here more energy is coming from the high temperature plate is giving more energy. At the same time, it is receiving lesser energy. Supposing I am the high temperature plate, there is a low temperature plate in front of me. I am giving more energy to that. At the same time, while I am giving in one hand, I am receiving some energy coming from the low temperature. But the rate which I am receiving is lesser as compared to the rate I am giving. Because my temperature is more, I am emitting more energy. All bodies at all temperatures emit radiation. The rate of emission is directly proportional to the fourth power of the absolute temperature of the body. If the absolute temperature gets doubled, the rate of emission from the body will increase by 16 times. So, the high temperature body naturally will emit more energy because it is proportional to the T to the power of 4. And the low temperature body also emits but emit lesser. So, it is giving more and receiving lesser, therefore, the high temperature body keep on decreasing. Low temperature body, what will happen? It receiving more but giving lesser, therefore, its temperature keep on rising. After a certain stage, both of them will come to the thermal equilibrium. After a certain time, both high temperature and low temperature body comes to the thermal equilibrium. At that instant also, the giving and the receiving keeps continuing. But whatever I am giving with one hand, exactly same amount of energy I am receiving from with the other hand. Therefore, my my temperature remains constant. That is called steady state. Steady state energy heat transfer conditions. Okay. So, temperature will not change because I have arrived at the thermal equilibrium. Okay, I arrived at the thermal equilibrium with the other plate. Whatever I am giving, exactly same amount of energy I am receiving. So, energy is balanced. So, no further change in temperature because I have arrived at the thermal equilibrium with the other body, that is other plate. Mind that after achieving the thermal equilibrium also, same temperature also, this giving and receiving will continue, but the rate of energy giving and the rate of energy receiving are exactly equal, right. So, this is the radiation mode of heat transfer. Best example for the radiation is, just example, from the sun to the earth, from the sun to the earth, there is a lot of vacuum. There is a lot of vacuum present in between. So, how do the radiation happens? How do the radiation happens? By electromagnetic waves. Radiation happens by electromagnetic waves, which can propagate even through the vacuum. Between the sun and the earth, we have the only atmosphere up to certain level, certain boundary. After that, it is all vacuum. But through that vacuum also energy is propagating, because we are receiving the sun, earth is receiving the energy from the sun by electromagnetic wave propagation called as the thermal radiation. Best example for the thermal radiation is propagation of heat energy from sun to earth. Okay. So, at any given instant of time, all the three modes of heat transfer may simultaneously be there. Best example is our human body is there. If somebody asks you what is the mode of heat transfer between the body and the surrounding air, your immediate answer is convection. But my answer is radiation also will be there, but that fraction is very, very small. We neglect that. There is a radiation energy also is there, a radiation heat transfer also. My body is losing heat to the surrounding atmosphere not only by the convection, but there is some fraction of radiation energy also will be there, but we are not considering that in the problems. We consider only usually convection. Okay. So, all the three modes of heat transfer may be simultaneously there at a given instant of time. For example, there is a solar flat plate collector. For example, there is a solar flat plate collector, solar water heating system, sun. Nowadays, people are using on the roofs, roofs of the buildings. This is an absorber plate. So, plate will receive the energy from the sun by radiation. Majority of that, and almost 90% of energy will get absorbed by the absorber plate. Around some part will be reflected, maybe reflected there. Most of the energy will be absorbed. That heat energy will get conducted through the plate. What happens? And here I am circulating water. I am circulating water. This is all water. So, what is the mode of heat transfer here? Convection. There is a radiation heat absorbed. There is a conduction through the plate and again convection to water. This is a water heating system. Convection to water. So, all three modes will be there in any heat transfer problem. Two modes or sometimes all the three modes we need to consider. So, these are the modes of heat transfer. Now, I will give the governing laws of heat transfer. All the three modes are governed by three distinct laws, which is called as the conduction is governed by Fourier law, convection is governed by Newton's law of cooling, radiation is governed by Stephen Boltzmann law of radiation. There are three distinct laws governing three different modes of heat transfer. Conduction is governed by Fourier law of conduction. The law states that the rate of heat transfer by conduction along a given direction is directly proportional to temperature gradient along that direction. Temperature gradient along that direction, and is also directly proportional to area of heat transfer lying perpendicular to the direction of heat transfer. Lying perpendicular to the direction of heat transfer. It could be understood easily by seeing this figure. Suppose that there is a one slab. There is some slab is there. One side of the slab is maintained at a temperature of T1 and the other side is maintained at a temperature of T2. T1 is greater than T2. There are temperature gradients existing inside that slab. One side of the slab is at T1, the other side of the slab is at T2. This is the x direction. This is the x direction. Direction of x is this way. The law states that the rate of heat transfer is in this direction. The rate of heat transfer is a vector quantity which always occurs in a direction in which the temperature is decreasing. What is the direction of heat transfer if somebody asks? We should say that what is the direction of heat transfer if somebody is asked? We should say that heat always flow from the high temperature to the low temperature. So, the direction in which the temperature is decreasing is the direction of heat transfer. T1 is greater than T2. So, the rate of heat transfer, this is a standard symbol I use. The rate of heat transfer is directly proportional to the temperature gradient. What is the temperature gradient? For a differentially small increment in x, what is the drop in temperature? dt by dx. As dx approaches 0, what is the temperature drop? If you just consider two planes which are differentially close to each other, between those two planes, what is the temperature fall? The planes are too close, the gap between them is tending to 0. So, that temperature fall between those two planes can be thought of as a temperature gradient. Minus sign only shows that as x is increasing, temperature is decreasing, and is also directly proportional to the area of heat transfer lying perpendicular to the direction of heat transfer. Remember, in every conduction problem, the direction of heat transfer and the area of conduction, the direction of conduction and the area of conduction must be perpendicular. They are normal. Remember that. So, the proportionality constant is K, thermal conductivity of the material of the slab. K is the thermal conductivity of the material of the slab. This is called as the Fourier law of conduction. Ka minus Ka dt by dx. K is the thermal conductivity property. This is thermal conductivity of slab, a property of material property. Okay. Minus sign only shows that as x increases, temperature decreasing. So, that is the, so Fourier law defines the conduction. Now, I define the Newton's law of cooling. There is a hot plate over which a colder fluid is coming with a some temperature and maybe some velocity. It is a forced convection, I suppose. There is a heat transfer happening. The law states that the rate of heat transfer between a solid body and a surrounding fluid the rate of convection heat transfer, more correctly, the rate of convection heat transfer between a solid body and the surrounding fluid is directly proportional to the temperature difference between them is directly proportional to the temperature difference between them and is also directly proportional to the area of contact, area of touch, wherever the fluid is in contact with the body, yes, that is the area of convection. Convection area is very simple to imagine. Conduction area is the area perpendicular to the direction of heat transfer. Then how do you imagine the convection heat transfer area? Wherever the fluid is in contact with the solid body, we may take it as the convection area. Area of contact or area of touch. Area of touch between body and fluid. States that Q is the standard symbol. I use it for the rate of heat transfer. The law states that it is directly proportional to the temperature difference between them and is also directly proportional to the area of contact. Area of contact means area of touch. Wherever the fluid is in contact with the body, that is the area of convection. So, the proportionality constant will be H. HA delta T. This is called as the Newton's law of cooling, basic law behind the convection. Okay. This H is called convection heat transfer coefficient. In the entire convection chapter, we always try to calculate this. Units watt per meter square Kelvin, not a property. H is not a property. K was a property. Material or medium. Okay. K is a property but not the H. Okay. Now third one. Stephen-Boltzmann law of radiation. For the third, Stephen-Boltzmann law of radiation. It is the law governing the radiation. The law states that the radiation energy the radiation energy emitted. Everybody emits energy. You emit, I emit, the wall emits, the floor emits. Everybody at every temperature will emit thermal radiation in the form of electromagnetic waves, which can travel even through the vacuum. Everybody at every temperature emits. But that rate of emission per second we are giving that energy, how we are emitting in the form of photons, or rather you can say in the form of waves, electromagnetic waves. A wave is carrying the energy. But the rate at which energy we are emitting is mainly dependent upon the absolute temperature of the body. If the absolute temperature of the body gets doubled, the rate of emission from the body will increase by 16 times. That is why T to the power of 4. If the absolute temperature of the body gets doubled, the rate of emission from the body, the rate of thermal radiation emitted from the body will increase by 16 times. The law states that the radiation energy emitted from the surface of a black body is directly proportional to the fourth power of the absolute temperature of the body. Is directly proportional to the fourth power of the absolute temperature of the black body. What is this black body? In radiation chapter, black body plays a very important role. Black body is the body which absorbs all the thermal radiation falling on that. Black body is the body which absorbs all the thermal radiation incident or falling on that. No reflection, no transmission, only absorption. But don't come to a wrong conclusion that black body means when you see that it looks black. No, wrong. Thermal blackness, visible blackness are different. Ice is there, ice, barf, ice or snow, they are thermally black, but they appear white to our eye. So don't get confused with that word black. A thermally black body which is absorbing all the radiation, swallowing all the radiation, absorbing all the thermal radiation may not appear black in color to the human eye. Best example is ice and snow. They are thermally black, but they don't appear black when you see them. Ice doesn't appear black, but thermally it is a very good absorber of heat. It absorbs all the thermal radiation falling upon that. Okay, EB is the emissive power. This is also later called emissive power. The proportionality constant is called sigma. Sigma is called Stefan-Boltzmann constant. Its value is 5.67 into 10 power minus 8 watt per meter square Kelvin to the power of 4. In all the radiation problems we are going to use this. Right, now we have seen the all the three governing laws. Now I will integrate the Fourier law of conduction. Now we will go back to the I will define now thermal resistance concept from this integration of Fourier law of conduction. Supposing if this is the slab, okay, and B is the width of this slab, K is the thermal conductivity of the material of the slab, this is the X, right, this is dt by dx. this gradient. B is the total width of the slab. A is the area of conduction. Qx is equal to minus Ka Qx into dx minus Ka dt. Okay. Now we have to make some assumptions here. Generally, in the analysis of heat transfer, you require the assumptions. Always you have to write. If you write the assumptions in the problem of heat transfer, you can bag complete marks. Never forget to write the assumptions, particularly in the subject heat transfer, even when you are solving the problem. Problem solving also we have to write the assumptions. Assume steady state heat transfer conditions. What do you mean by steady state heat transfer? Temperature at a particular location is not a function of time. Temperature within the body at a particular spot do not change with time. Number 2, one-dimensional conduction. Heat is conducting only along x because in that direction only we have the temperature gradient. Constant K, uniform thermal conductivity. It is not the variable conductivity, it is uniform thermal conductivity. So now we can integrate this 0 to B, T1 to T2. So to satisfy this steady state, heat transfer, Qx should be equal to the Qx plus dx. Qx should be equal to the Qx plus dx. That is, Q is not a function of x. At every location, the value of the Q should be the same. Why so? If you take a differentially small increment in x, whatever the heat that is entering into that differentially small element of the slab of thickness dx, if you just take the small differential thickness of the elemental thickness of the slab, whatever the heat that is conducting here, same amount of heat must conduct here. Whatever the heat that is conducting here, say 10 joules are entering in 1 second, say for example, 10 joules are entering in 1 second. In the same second time, 10 joules must leave. That is called as the steady state. Q should not be a function of x. When Q is not a function of x, we can take it out. K is also a constant, Ka delta T by B. This is the integrated format of the Fourier law of conduction. Delta T is the temperature difference, that is T1 minus T2, right? This is the rate of conduction heat transfer through slab. Okay, so this is the formula. Many times we calculate the flux, heat transfer rate per unit area. It is also called as heat flux. Flux means per unit area. If area is not mentioned, most of the times he will not mention, we always calculate flux in watt per meter square. Heat flux means heat transfer rate per unit area. Okay. Now in this concept, I will define a thermal resistance concept or electrical analogy. Or electrical analogy of heat transfer. In this analogy, electrical terms on one side, thermal terms of I is analogous to the Q. I current, no? Why the current flows? Delta V. Delta V, why the heat transfer is there? Temperature difference. What is the reason behind the flow of electric current in the electric circuit? Voltage difference or a EMF or delta V. We have the electric resistance here in ohms. Correspondingly, we have thermal resistance. If this is the electric circuit, this is the thermal circuit. Temperature difference, delta T. T1, there is a thermal potential. Flowing current is heat transfer rate. This is the thermal resistance. Now here, the electric resistance, this is delta V. Flowing current is I. This is the electric resistance in ohms. Okay, I is the current. Here the I is analogous to the Q. Electric resistance is analogous to the thermal resistance. Voltage difference, voltage difference is analogous to the temperature difference, delta T. T1 minus T2. This difference. Now, from Ohm's law, we know that electric resistance is equal to delta V by T, delta V by Q. E by R is equal to Q or electric resistance. Similarly, thermal resistance delta T by Q, so many degrees Celsius per watt or Kelvin per watt also we can write. So now I define the very important definition called as the thermal resistance, delta T by Q. So now this thermal resistance concept I would like to make use of for calculating heat transfer rate through a composite slab. Conduction heat transfer through a composite slab, a slab consisting of more than one material. So look at this. This is a slab consisting of two different materials. Okay. This is B1. K1, K2, two different materials. This is the direction of the heat flow. These are the temperatures. This is the T2 or T interface. T2 is the T temperature at the interface. Junction. Okay, now we have to construct the thermal circuit assuming the steady state standard assumptions. See, the most commonly used assumption in heat transfer is steady state heat transfer, that is temperature will not change with time. Thermal circuit comprises two resistances in series. Why in series? Unless the heat current flows through this, it cannot enter here. One after another. First conduction through this slab and then conduction through this. T1, T2, T3. What is the first resistance? B1 by K. B1 by, from this from Ohm's law, look at this earlier. I forgot to tell you, this is from this. What is delta T by Q? Delta T by Q will be B by Ka. Okay, this will be, I forgot to write there. This will be equal to B by Ka formula, thermal resistance formula. This is a general thermal resistance. So, conduction thermal resistance formula for a slab, it will be B by Ka, because that is equal to the delta T by Q. You can see here, delta T by Q means T1 minus T2 by Q will be B by Ka. Now, the second resistance will be B2 by K2A. A is same throughout, B2 by K2A. The rate of heat transfer will be conduction heat transfer through wall. It will be so many watts. Rate of heat transfer is always in watts. Supposing many times you want to calculate the interface or the junction temperature. We know the current. This junction temperature, if you want to try it, take this potential difference or this potential difference. Therefore, current already it is there, T1 minus T2 by, from this interface temperature can be calculated. This is for the composite slab. Now, I do the conduction heat transfer, radial conduction heat transfer through a hollow cylinder. Like this. There is a hollow cylinder with the inner and outer radius. Inside temperature is T1, outside temperature is T2. Say T1 is greater than T2. A hollow cylinder. L is the length of the cylinder. Here T is a function of R, because this is the direction of the conduction. This is the direction of the conduction, radially outwards. Okay. This is the direction of the radial conduction. The heat transfer is happening radially outwards. Now, if you write the Fourier law, minus Ka dt by dr, temperature gradients are existing along the radial direction. Okay. Inside temperature is T1, outside temperature is T2. So, heat is conducting radially outwards. K is the conductivity of the material of the cylinder. At any radius R, that is the area, 2 pi RL is the area perpendicular to the direction of heat transfer, minus Ka dt by dr, that A is the radial conduction heat transfer area perpendicular to the radial conduction at any radius R. At any radius R measured from the axis, 2 pi RL is the area perpendicular to the direction of heat transfer. The area perpendicular, see, look at this, but the area perpendicular to the direction of heat transfer at the inner surface will be 2 pi R1L. The area perpendicular to the direction of heat transfer at the outer surface will be 2 pi R2L. That means unlike in case of the slab, in case of the slabs, in the direction of the heat flow, the area of conduction heat transfer will not change. In case of the conduction heat transfer through the slab, the conduction is happening like this. But the area of conduction here and here, it is same. In the direction of the heat flow, it is same. But unlike that slab case here, in case of the radial conduction heat transfer, area of conduction heat transfer changes. That is why as R changes, area of conduction heat transfer also changes. Q into dr by R is equal to minus 2 pi KL dt. Now we could integrate this with the help of assumptions. We can integrate R1 to R2, T1 to T2. The same assumptions will hold good. Steady state heat transfer, one dimensional conduction, radial conduction, constant के same assumptions like in case of the slab. Same kind of assumptions. Steady state, one dimensional radial conduction and constant thermal conductivity. Now after integration you get the rate of heat transfer will be T1 minus T2 2 pi KL Now if you construct the thermal circuit here, flowing current is Q, this is the thermal conduction for the radial conduction. Radial conduction heat transfer, radial heat transfer through hollow cylinder. Now I am putting the second resistance. For hollow cylinder it will be ln R2 by R1 divided by 2 pi KL, so many Kelvin per watt. Earlier I had given one resistance, that is B upon Ka. For a slab, B upon Ka. For a hollow cylinder, it is ln R2 by R1 divided by 2 pi KL. This is the second one. Now I am going to give the generalized convection thermal resistance. What is the convection law? Basic law, Newton's law of cooling. Q is equal to HA delta T. Therefore, delta T by Q is equal to convection thermal resistance. It will be 1 upon HA. So the third resistance I am giving. Until now I had given the 2 conduction resistances and 1 convection resistance. 1 convection resistance, that is 1 upon HA, and 2 conduction resistances, right. Now I could give the concept of the conduction heat transfer. Conduction, this is a most commonly asked questions in K2 examinations. Conduction, convection, heat transfer through a composite slab. It is a very commonly asked question, very commonly, like this. Sometimes there may be 2 materials, sometimes there may be 3 materials, but this side hot gases are there, this side colder fluid is there. So the heat transfer is happening in this direction. What is the mode of heat transfer from between the hot gases and this side? It is by convection. Whenever there is a convection, how do you notify? By using convection heat transfer coefficient. Whenever you talk about the convection, the coefficient we speak immediately, we indicate that convection by H. Later when we enter the convection chapter, calculation of H was the prime objective. This is the material conductivity K1, K2. Again this is the convection with H2. So this is the direction of heat transfer. So in this is B1, same assumptions. Assume steady state one dimensional heat transfer. Assume steady state one dimensional heat. Now between Tg and this side colder fluid, colder fluid temperature is T infinity. We have to give the figure like this. If you give the figure like this for the problem, the things will be better. So Tg is much greater than the T infinity. So between Tg and T infinity there is a heat transfer happening. How many resistances you may expect? There will be 4 resistances. Convection, against the heat current there is a convection, there is a conduction here, there is a conduction here, and again there is a convection. There will be in total 4 thermal resistances. If you construct the thermal circuit, first convection, conduction, conduction, and again convection. Tg and this is T infinity. First thing is the left side convection, then conduction, and finally right side convection. So these temperatures also you need to mark. Tg, this is T1, junction is T2, and this is T3. T1, T2, T3. This is T infinity. So in the thermal circuit, this is T1, T2, T3. What is the first resistance? 1 upon H1A. Let us mark. In case of the slabs, area of heat transfer will not change in the direction of the heat flow. He then comes B1 by K1A, then comes B2 by K2A, then comes 1 upon H2A. Flowing current is Q, the rate of heat transfer. So the rate of heat transfer between hot gases and colder ambient, between hot gases and colder fluid, right side colder fluid is there, right, will be Tg minus T infinity divided by 1 by H1A plus B1 by K1A this is the rate of heat transfer through the between the hot gases and the colder air. But most of the occasions we always calculate heat flux only. Flux means heat transfer rate per unit area. Majority of the cases they ask flux only. Sometimes area may be given, fine, we will consider that. So this is the rate of heat transfer or heat flux, rate of heat transfer per unit area. If this is in watts, this is in watt per meter square because you brought the area left side. This is in watts, here it is watts per watt per meter square. Now from this we could define what is the overall heat transfer coefficient. What is overall heat transfer coefficient? It will consider all effects, considers all effects of all modes of heat transfer, conduction, and put into considers all effects of all modes of heat transfer and it put into single parameter and defined from Q is equal to UA delta T. Here, in case of the composite slab with convection on both sides, it will become 1 by H1 plus B1 by K1 plus B2 by K2 plus 1 by H2. U actually H I defined already. H is the convection heat transfer coefficient. U and H have same units. U and H have same units, that is watt per meter square Kelvin. But H speaks about convection only, U takes care of all modes of heat transfer. So, this is the formula for overall heat transfer coefficient in case of the composite slab subjected to the convection on both sides. Two conductions and the left side convection, right side convection. Now, we may take a break for about 5 minutes. Hello students, now this is a question given in KTU, one of the recent KTU examination. Derive generalized conduction equation in Cartesian with neat sketch. Yes, this is the derivation which I am going to do. Generalized conduction equation. I took a small differential elemental of the slab. This is the x coordinate, this is y coordinate, this is z coordinate. There is a uniform heat generation. Q dot is the uniform heat generation rate. Heat is being generated throughout the slab. I have considered a dx amount of the element of the slab. There is a uniform heat generation. I took a small differential element. Consider differential element of slab of thickness dx. If Qx is the heat conducted along the x direction and Qx plus dx is the heat conducted out of the element along the x direction, Qx could be written as from the Fourier law minus Ka dt by dx, where A is the area of conduction. Then Qx plus dx, because this is a generalized conduction equation, I don't have to make any assumptions there. I am permitting the temperature to change with time. Steady state means what? Temperature at a particular location must not change with respect to time. But now I am giving the generalized conduction equation, so I am permitting the temperature also to change with the time. And heat generation is also there. Throughout the slab, heat generation is there, throughout the slab. Okay. So, Qx plus dx may not be equal to the Qx. In the earlier case, I said Qx is equal to Qx plus dx to satisfy the steady state heat transfer conditions. But now I am permitting the unsteady state conditions also. Conditions may be steady or unsteady. Therefore, the Qx and Qx plus dx may not be equal. In such case, it should be written as Qx plus dou by dou x of Qx into dx. Try to understand. Dou by dou x of Qx is the rate of change of Qx, because Qx may be a function of x. This is x direction, right? So, dou by dou x of Qx is the, for a differentially small increment in x, what is the change in Qx? That is dou by dou x of Qx. When that is multiplied by dx, we will get the total change in Qx for a distance of dx. Dou Qx by dou x is the rate of change of Qx for a differentially small increment in x. When the rate of change is multiplied by dx, you will get the total change in Qx for a distance of dx. Add that to the Qx to get the Qx plus dx. Heat generated, Q generated in element. Q dot is generated per unit volume, clearly mentioned there. That is, what is the volume of the element? Q dot into volume of element. Volume of element will be ADX. Q dot into ADX. ADX is the volume of the element. Now I write in the energy balance for x direction conduction. Now writing the energy balance for x direction conduction. Energy balance means the rate of the energy can neither be created nor destroyed. Writing the energy balance. What is entering into the element is Qx. What is generated in the element is Q dot into ADX. What is entering into the element is Qx. What is generated within the element per second is Q dot into ADX. That is one side. What is going out of the element is Qx plus dx. And what is the balance? There is something entering. Supposing this is the element. There is something entering into the element. There is something generated within the element. There is something going out. What is entering and what is generated within the element, that is one side. And supposing 100 entering, 50 are generated. 100 plus 50, 150. Out of which say 75 is going out. So 150 minus 75, the remaining 75 must stay back, must return back, must be picked up by the element, which will be used to increase its internal energy. There is 100 watts entering, for example, 50 watts are generated in the element. Due to generation means because of some other energy is getting converted into heat, maybe electrical form or a chemical form. Energy can be generated, heat can be generated in so many ways, by chemical reaction, by electrical power, etc. So heat may be generated throughout the slab. What is entering is 100, generated is 50. Suppose that 75 is going out. 150 minus 75, the remaining 75 must be taken or swallowed by the element, which will be used to increase its internal energy. Rate of increase of internal energy of element with respect to time. So that could be written as Qx plus Q dot into ADX. What is Qx plus dx? Qx plus dou by dou x of Qx into dx plus what is the rate of change of energy? Dou by dou tau. Tau is the symbol I am using for that time, mCp into t. Tau is the symbol I use it for the time in seconds. Small t I can use, but I write for tau symbol for where m is the mass of element. Mass of element will be rho into ADX. Now Qx gets cancelled. Q dot into ADX is equal to dou by, I have write the Fourier law of conduction, minus Ka dt by dx into dx plus dou by dou tau of rho into ADX into Cp into temperature. ADX gets cancelled. So if you rearrange the parameters, dou square T by dou x square, dou square T by dou x square left side plus K is there, K into plus Q dot is equal to rho Cp into dou T by dou tau. Rho Cp is a constant, right? All the properties are constant throughout the subject. Throughout the subject of heat transfer, there are 4 properties we deal with: rho, Cp, K and viscosity if it is a fluid. Only 4. Density, specific heat, conductivity, mass is equal to rho into volume. This is the rate of change of internal energy of the element, which is given with respect to the time. This is the internal energy of element, right? So this is the energy balance for x direction conduction. But if you just look at the figure, heat may conduct also in the y, heat may also conduct in the z. Now what we have written is the x direction conduction. So if you generalize the conduction equation for all the directions, for all 3 directions, if we write similarly, all conductions put together, the energy balance. Now what we have written is the only for the x direction. If you write for all the 3 directions which are happening simultaneously, conduction along x, conduction along y, conduction along the z, we get K into dou square T by dou x square plus K into dou square T by dou y square plus K into dou square T by dou z square plus Q dot into rho Cp dou T by dou tau. If you just divide throughout with K, plus Q dot by K. Q dot is always the symbol Q dot for the heat generation per unit volume, dou T by dou tau, tau for the time. Here I define one important property called thermal diffusivity alpha, that is K by rho Cp. What is this? That is the thermal diffusivity, thermal conductivity divided by thermal capacity. Rho Cp's are is called as the heat capacity alpha. Alpha units are meter square per second. Please write that. This could most of the papers they may ask the definition. Thermal diffusivity alpha is defined as thermal conductivity by thermal capacity. If you substitute that alpha there, you get the final format of the generalized conduction equation. Plus Q dot by K 1 by alpha into. So, this is the generalized conduction equation. Remember this. Now, in the question he has asked, in that university question he has asked, reduce the equation for steady state, one dimensional and without heat generation. Steady state, one dimensional without heat generation. That means Q dot is 0, no heat generation, without heat generation. Okay. Steady state means things will not, what is the meaning of steady state? Steady state implies dou T by dou tau will become 0, no variation. Steady state means temperature is not a function of time, and one dimensional means T is only a function of x. So, therefore, this will become 0, this will become 0, this will become 0 and this will become 0. So, you get the result will be dou square T by dou x square is equal to 0. This is the final format of the equation. Okay. Right. Now, this is a question asked. Actually, some question students are asking, do the problems actually. No, I will do the problems, because you see, to do the problems, once you should have the basic concepts of the fin, right? Unless otherwise you have the concepts of the fin, just knowing the problem also may not help you. I just tell you something how to analyze the problem. Fin is a projection from a wall that is meant for increasing the heat transfer rate. A fin, here also a rectangular fin. A rectangular fin is a projection from a wall which is meant for increasing the heat transfer. T naught is the base wall temperature, standard notation, base wall temperature. T infinity is the fluid temperature. From the heat is first conducted here. The mechanism of heat transfer is first heat gets conducted here from the base wall, only conduction, and then it keeps conducting here. At the same time, heat also getting convected. This is convection. With convection means immediately H strikes. Convection means H must be there. So, that most of the fin problems we assume that the tip is insulated. See, the tip of the fin is insulated. This is insulated. See this. Most of the fin problems assume that, by default assume that. L is the length of the fin. Z is the width of the fin. This is the Z. T is the thickness of the fin. All the three dimensions will give it. Rectangular of cross section 8 into 3 cm square. This is maybe 8. This is the area. Area of the cross section on 8 here will be 8 into 3 centimeter square. We will convert into the meter square there. 8 into 3 into 10 power minus 4 meter square. This is the cross sectional area, okay, of the fin. This you can indicate this actually. This is the cross sectional area. I would like to indicate this is the cross sectional area. This area, hatched area. Fin base is maintained at 400. Okay, and the ambient temperature T note fluid temperature is 30, room temperature air temp. Fin, because by default the fluid around the fin will be gas, mostly air, atmospheric air. You don't have to consider any other fluid. Take it as always atmospheric air. This is a cross sectional area. Okay, A. Now, what is calculate the heat transfer rate from the fin? Generally, in the fin problems, we come across two distinguished cases. One is fin is infinitely long. One is fin is finite in length like this. What is the length of the fin? 1 meter is given. Length of the fin is 1 meter. Fin is 1 meter long. and finite in length, and tip is insulated. That is one important case. There is another important case of the fin is infinitely long, very long fin. So, for those two conditions, the formula for calculating heat transfer rate will be different. Here I calculate the heat transfer rate through fin. Square root of Hp Ka into T naught minus T infinity into tan HML. This is a hyperbolic tan, it is not the convection coefficient. Please note that it is the hyperbolic function. In calculator, we have to look for the hyperbolic tan. What is that? M is equal to root of Hp by Ka. Root of P is the perimeter. P is the perimeter of the fin. What is perimeter of the fin? This is the perimeter. This round is the perimeter. If it is a fin is, if the fin is circular, which is called as the pin fin, perimeter will be, if d is the diameter of the fin, perimeter will be pi d. But here, what is the perimeter? 2z plus 2t. 2 into z plus t. What is the z value there? 8 plus 3 divided by, that is centimeter, that by, divided by 100 meters. This is the perimeter of the fin. We know the perimeter, conductivity of the fin, aluminum. Assume the conductivity of the aluminum is not given. Data book, if it is permitted, you can take it. You can assume otherwise. Even if you take the data book, if the data book is permitted in the exam, there will be tables will be there in that conductivity of various materials. But aluminum is a very great material. We should remember conductivity is 200. I know the K, H is given as how much? H is given as 10. This H is given as 10. Okay. That is M is equal to square root of 10 into okay, 2 by 100 into 8 plus 3. That is the perimeter. Conductivity is 200. That is 8 into 3 into 10 power minus 4. That units will be per meter. M units will be per meter. Length I know. Length is already 1 meter I know. M I know. K value given. Area, of course, area is H is given. H is 10. Perimeter there. You will get the rate of heat transfer through fin in watts. Just substitute there after getting first step in calculating the heat transfer. In any fin problem, remember, in any fin problem, first step what we need to calculate is the M value. What is M value? Root of Hp by Ka. P is the perimeter. If it is a pin fin, pi d, and A is the, what is the area here? Pi by 4 d square, if it is a pin fin. Okay. And another important formula we may remember for the fin will be heat transfer rate for very long fin. For very long fin, infinitely long fin, it will be square root of Hp Ka into T naught minus T infinity watts. So, this formula for a very, but this is for a long fin. Earlier case was a finite length in fin. And one more thing, for the fin efficiency, we have to remember, it is tan HML by ML for the insulated tip case. For the early insulated tip case is a very important formula for in case of the fin problem. Tan, remember these two formulae also, tan HML by ML there. L is the length of the fin. And one more performance also is there, effectiveness of fin. Effectiveness of fin will be Q with fin by Q without fin. These are the another performance of the fin. How do you define efficiency? Actual heat transfer rate divided by heat transfer rate from fin if entire fin is at base temperature. if entire fin is at T naught. That is the definition of the fin efficiency. This is the effectiveness. Two are different things. This is the definition for the fin efficiency. This is for the effectiveness. Please remember these two formulae. If at all anything is asked about the fin, three things they may ask. Heat transfer rate through the fin, number one. Efficiency of the fin, number two. Effectiveness of the fin. Efficiency of the fin is actual heat transfer rate through the fin divided by heat transfer rate that would occur from the fin if the entire fin is at the base temperature or the root temperature. Actually in the fin, supposing this is a fin attached to the wall, from the base wall to the tip temperature will drop. Temperature will drop even though fin is made up of a good conducting material. If this is a fin is attached to the base wall, there is a drop in temperature along the length of the fin. In case if the material of the fin has got infinite conductivity, then the temperature drop will not be there. Same base temperature you will see all along the length of the fin. Under that idealized condition, if the conductivity of the material is infinity, that means no drop in temperature, say throughout the fin same T naught. Under that idealized condition, what is the heat transfer rate? That is the maximum possible heat transfer rate. That is also defined as Q actual by Q maximum possible. Q maximum possible heat transfer rate. Okay, right. Like this. This is another problem given in previous KTU, Kerala Technological University. An electric cable of 10 mm. First thing, what we have to do in any heat transfer problem is to score maximum marks. I will give some clues. But always in this heat transfer subject, given problem, it transform into the figure. Figure is a must, number one, whatever may be the chapter, conduction, convection, radiation or heat exchangers. Given problem, it put everything into a figure and in the figure itself show the data, number one. Number two, write the assumptions. Compulsory, write the assumptions. Give the figure, write the assumptions, all the parameters neatly calculate, and after writing the formula and any conclusion or any comment about the answer, why the answer is like that, why not some other way, anything also if you can mention at the end, you will if the problem is set for 10 marks, complete 10 marks you may bag. Usually problem will be given for 8 or 10 marks. All 10 marks you can score. Figure must be there like this. An electric cable of 10 mm diameter is to be insulated by a rubber. This is the rubber. Okay. Assume cable, this is a cable, that is rubber. Cable surface temperature is 70 degrees Celsius. Surrounding air temperature, we always use the symbol T infinity, that is the air temperature is 30. Convective heat transfer coefficient, where the convection is happening between the rubber surface and the air. Convection always occurs between a solid and a fluid. This is the convection. You are talking about convection means H should be there. What is a H? 10. 10 watt per meter square Kelvin. Find the critical thickness of insulation. This is a problem on critical radius. This is a problem on critical radius. Okay. What is this critical radius and what is its significance? First, let us understand what is the meaning of critical radius and what is the significance of that critical radius of insulation. Critical radius of insulation is given by K of the insulation divided by H. What is the meaning of that? That could be understood by seeing this graph. They may ask the significance of the critical radius in the theory questions also. Critical radius of insulation is the radius put around a cable or a wire. There is a thin wire. Around that some insulation is wrapped. What is the critical radius of insulation is, after wrapping the insulation, that radius where the heat transfer rate has become maximum. That is called as the critical radius of insulation given by this formula. Generally people always think that commonly we think that if you have a wire, if you put the insulation around that, heat transfer rate will decrease from the wire to the air. But that is not always, that is the general thinking, that is correct also, most of the occasions, but some cases that may not be correct. But there are few cases where if the radius of the cable or the wire is very small, the radius of the cable or the wire is very small, very thin wire, if you put the insulation, after putting the insulation, heat transfer rate will be more as compared to the case where there is no insulation. So that is the concept of the critical radius of insulation. After putting the insulation, heat transfer rate will be, as you keep increasing the insulation, more and more insulation, heat transfer rate also increasing. See this graph? See this graph. As you are putting more and more insulation, heat transfer rate keep on increasing and becoming a maximum at the critical radius, and after that it again begins to fall. So critical radius of insulation given by this K by H is the radius where the heat transfer rate is maximum from the cable. Now in this case, what is the K of the rubber? This is the K of the rubber given. What is that? 0.14. What is the H value given? 10. Okay, 10. This is 0.14. So many meters. But generally, this usually it may be it can be converted into the millimeters there. Okay, okay, but you can keep it like this. And this is only critical radius. This is the critical radius where the heat transfer rate is maximum. But he didn't ask that. He has asked, look at this. He has asked the critical thickness. Critical thickness means we have to subtract the, this is the critical thickness. Therefore, critical thickness of insulation will be 0.14 by 10. From that, you have to subtract the radius of the cable minus, what is the radius of the cable? 10 mm diameter. That means radius will be 5 mm. Of course, 5 mm means 5 by 1000 meters, because this answer is in meter. So we have to take care of the units there. So this is the answer. But generally, value being very small, you multiply that into the 10 cube to express the answer in millimeter. So this is the answer. And find the critical thickness of insulation and compare the heat transfer for with and without insulation. Yes, see that now with and look at the second question. Heat transfer rate without insulation and heat transfer rate with this insulation. We have to compare. First I calculate without insulation. Q without insulation. No, there is no rubber at all. Only cable is there, no rubber. This is only cable. Directly it is losing heat by convection. Convection with H. H, what is the Newton's law of cooling? H area of convection into delta T. H is 10. What is the area of convection? Pi dl. What is the temperature of the surface? 70, right? 70 minus 30. Okay, diameter we know. Diameter of the cable is given 10 mm. This is 10 mm. Length has not been given. You can take per unit length. If the length is not mentioned, in any case, if the length is not mentioned, take it as 1. Generally, particularly in case of the cylindrical cases, sometimes length may not be given. That is 10 into pi into diameter is 10 by 1000, length you can take it as 1 into 40. So, this is the rate of heat transfer without insulation. Then Q with insulation, with a critical insulation, that is delta T divided by, we have to add two resistances there. In case of generally cable is there, in the cable around that we have kept the insulation, right. We got the insulation here, we got two resistances here. If you just take, there is a conduction here, there is a convection here. There are two resistance. What is the first resistance conduction here? Ln R2 by R1 divided by 2 pi KL, plus outside there is a convection resistance 1 upon H into, this is R1, if you take, this is R2 after putting the rubber, 2 pi R2L. Now let us delta T is 70 minus 30. First let me keep what? R1 will be 5 mm, R2 will be, you have already calculated R2. What is that R2? This is R2. Calculate. This is 14 mm, R2 will be 14 mm. I know R2, I know K is thermal conductivity of the rubber. Rubber as thermal conductivity has been given, right? That is 0.14. 0.14, length is 1 meter you may take, H is 10, you substitute all these things there. But while putting here R2, the ratio no problem, but while putting R2 here, you have to convert 14 divided by 1000. Everything can put into the meter there. But here no problem. Logarithm of a ratio, no, you may keep both in mm. No, doesn't matter. You will get the with insulation. Definitely Q with insulation, if you see the answers there, is much greater than the Q without. You can see in the graph also. This is Q with insulation. This is Q without insulation. This value is much more, that you can see in the values also. Okay, but here please note that R2 convert into the meters. But whereas critical radius of insulation, I got it as the 14 mm. Okay. Right. So this is how we have to attempt the problems of the critical radius concept is very important in the conduction. In the conduction chapter, the most commonly asked topic is, main important is critical radius, number one. Number two is lumped heat analysis in the unsteady state conduction. Lumped heat analysis where we define the Biot number. So that kind of questions will be most commonly, and of course composite slab questions are very, very common in the conduction chapter. Composite slab, you know, where convection on both sides. Look at this. This is a composite slab only. This is a, look at this interior, a composite slab problem. This is composite slab with convections. H values are given, means convection on both sides. The interior temperature of a refrigerator. Walls are constructed with two mild steel sheets with 5 insulation between them. There are totally 3 are there. 2 mild steel, this is mild steel, this is mild steel, in between this is a glass wool packing. Okay. On the inner and outer, this say an interior temperature is maintained at 5 degrees Celsius. and outside temperature is in the kitchen room is 35, and heat transfer is happening like this from high temperature to the low temperature. This is a mild steel, you have to give the figure like this. And heat transfer coefficient on the inner side, this is inner side, inside of the inner side is 10. And outer side here, this is a convection, this is a convection, there is a convection here. Whenever there is a convection, H will be given 1.25. Okay, temperature in the kitchen room. Take conductivity of the mild steel is 40. Here also K is 40. Glass wool K is glass wool is an insulation, I already said. This is a glass wool, right? Sketch the electrical analogy. Like you have to give the figure like this. See, like this, how I am showing inner side and outer side. Like this, you have to show. If you show like this, there itself you can score some good marks. Assumptions. Assume steady state, one-dimensional convection, conduction, heat transfer. Through composite slab. This is a composite slab problem. The thickness are given to mild steel 3 centimeters. This is 3 centimeters. This is 3 centimeters. This is 5 centimeters. We have to show the data like this. This is 3, 3 in between 5. So this is the assumptions we have written given. Electrical thermal circuit. This is very important, particularly in the first chapter. Never forget this thermal circuit. So how many resistances are there? Totally 5. There is a convection here, there is a conduction, there is a conduction, there is a conduction, and again there is convection. CO and V I am writing, that is convection. Totally there are 5 resistances. Convection, conduction, conduction through glass wall, conduction, and again convection. Heat transfer is this way from high temperature. 35 to 5 degrees. This is convection. 1 upon HA, this side, first this side. That is 1.25. Area is not given, you can take per unit area. You look at this, very clearly mentioned, per unit area when kept in a kitchen room. Also find interval temperatures. Area we can take it as 1. So thermal resistance of the convection will be 1 upon HA. Thermal resistance of the conduction through the wall, it will be B by K. You remember the formula, B means thickness. So area is taken as 1. Then comes the conduction here, that is B by K. What is the thickness? 3 by 100, K is 40, area is taken as 1 because he has given area is per unit area. Then again conduction through the glass wool, thickness how much? 5. 5 by 100, K value is 0.04. Glass wool is insulation, very low K. Okay. Then again conduction for the mild steel again. 3 by 100. Why I am dividing with 100 is because centimeters I have to convert into the meters. Conductivity is 40. Area is 1. So finally we will have the convection. Finally we will have the convection, that is 1 upon H2 into A. What is that H2 there? This is 10. Area is 1. So the flowing current is from right to left like this. This is the heat transfer rate. Q is equal to 35 minus 5 divided by sigma, all the resistances. You will get the so many watt per meter square. 2 convection resistances, right side, left side. This is also convection. Rest of all are 3 conductions. 1, 2, 3, 2 convections there. Now he has asked the interface wall temperature. So you may call this, that means this temperature, you can call it as T1, T2, T3, T4. We want to calculate the T3. So you can mention that this is T1, T2, T3, T4. So we want to calculate all these four terms, T1, T2, T3, T4. Because heat transfer is this way, I have noted like this. Heat transfer is from high temperature to the low temperature. This is outer side, this is inner side. So how to get the T1? Current is current is same throughout series circuit. Current is equal to this potential difference divided by resistance. No, I have put up a wrong things actually here. Heat transfer is this way, no, right, 1 second. I'll just put a small mistake I have done, that heat transfer 35, heat current is going from, though figure is like this, heat transfer rate I marked that way. This one. Terminals I am changing. This is T1, this is T2, this is T3, this is T4. Because see, heat transfer rate between just 35 to adjacent, this is T1, T2, T3, T4, right. Now it's okay. Now the current is flowing in this direction from 35 to 5, 35 to 5. Now you can just take the any potential difference, this current. So to get the T1, Q is equal to get T1, Q is equal to 35 minus T1 by 1 upon H1A. 35 minus T1 divided by, what is the H1 there? Look at this H1, first one, 1.25. Like look at this H1 here. Though I have indicated here in the circuit, this is 35, right? 1.25 into 1. From this you will get the T1. After getting to get T2, heat transfer rate we know. T1 minus T2, T1 already known, divided by B by Ka of mild steel. Okay. What is the B by Ka? T1, you know, right. What is the 3 by K? 40 B by Ka. 3 by 40, right. T1 we already got it there. You substitute here. T1 minus T2 divided by 3 by 100. K is 41. From this you will get the T2. In the same manner, to get T3, from the T2 we can get the T3. Current is same. T2 minus T3 divided by, look at this, T2, this is this terminal, right. T2 minus T3 divided by this glass wool resistance, 5 mm and 0.04. B upon Ka, 5 by 100. Every centimeters we have to convert into the 0.04 is the conductivity, area is 1. From which we can calculate T3. You substitute this T3 here, T2 here, like that. Similarly, you can get T4. To get T4, current is same. We already calculated the current here. We already calculated in the earlier step. T3 minus T4 divided by the last resistance, that is same here is this. Again, 3 by 100 mild steel resistance, from which we can calculate T4 in degrees Celsius. So this T3 you substitute. First get the T1 here, put it here, then substitute that, get the T2, put the T2 here, then get the T3, put the T3 here, you will get the T4. Q we already calculated here, rate of heat transfer we already calculated. A simple analysis of the electric circuit. Give the figure, put the electric network, write the assumptions and solve the problem. You may comment upon that. Glass wool is a very good conductor. So, the temperature, so glass wool being a very good conductor, the temperature drop here, the temperature drop between the across the glass wool will be great. So, you can see the difference between T2 and T3 will be huge. Why? Potential drop will be very high. Why? Resistance is high. Current is same. Potential drop between 2 and 3 is high. Temperature difference between T2 and T3 will be high because the resistance offered by the glass wool is very high. That comment you may give. Delta T, T2 minus T3, right? Like look at this, across the glass wool, T2 minus T3. T2 minus T3 is high since thermal resistance of glass wool is high. That kind of comments you have to give. Why thermal resistance of glass wool is high? Glass wool is a very bad conductor. Key, see, right, if you just look at the materials here, mild steel you have. Mild steel is a conductor. Steel is a conductor metal. Glass wool is a very bad conductor. Very good insulator glass wool is. Generally in the refrigerator walls they use, and the air conditioner tubes outside they pack it. Puff also they use. Some other material used is polyurethane foam. That is even better insulator than glass wool. Puff they use in the air conditioner tubes in the refrigerators. Polyurethane foam, specially made foams are, because refrigerator temperature is low. You have to protect that low temperature. So inside the refrigerator walls they keep these packings, glass wool or a polyurethane foam packings. Okay, these kind of a comments are required. T2 minus T3 is high. If you give the comment like this, you will get the full marks. This is a convection problem. I am just looking for the conduction problem. These are all convection problems. This is the heat exchanger. This is also convection problem. Look at this. Define thermal diffusivity and explain its. This is the thermal diffusivity definition. Significance. It is a thermophysical property of material. What is the physical significance of this thermal diffusivity? It is a thermophysical property of material having the units of meter square per second. It is a thermophysical property of material. Thermal diffusivity alpha. Material which tells about the rate at which the heat energy could diffuse or pass through the medium. Pass through the medium. If alpha is more, means either K is high or heat capacity of material is low. Heat capacity or storage ability of material is low. So it has something connected with the time. How quickly heat energy can penetrate through a medium. Supposing it is like this. Supposing you have a hot oil. This is hot oil. two spheres of the same size are dropped into the hot air, two balls same size, but this has got more alpha of the material, this has got the lesser alpha. Then this will reach this material having more alpha can in a lesser amount of time it can come into the thermal equilibrium with the hot oil. Material having more alpha, same size, everything same, but this alpha of the material is more than this material. This material can come into thermal equilibrium of this hot oil in a lesser amount of time. It takes lesser time for this ball for the having more alpha to come into the thermal equilibrium more quickly. Very quickly it can come into the thermal equilibrium, whereas this material, this ball will take a lot of time to come into the thermal equilibrium. So there, because into this material heat energy can easily penetrate, diffuse or rapidly penetrate through the medium. Thermal diffusivity means it tells about the quickness or the rate at which heat energy can penetrate or diffuse through the medium or material. Discuss the effect of contact resistance on heat transfer and temperature distribution. Yes, this is a good question on the, supposing there is a composite slab. If there is a contact resistance between, here both the materials are in contact, right? Here if there is a contact resistance, temperature drop is there. If there is a contact resistance, there is definitely some temperature fall and then temperature. So this is the temperature fall at the contact between two surfaces due to contact resistance. Why this contact resistance happens is when the surfaces are joined, there cannot be perfect contact. There will be some voids will be there. This is some small, if the surfaces are in contact, this is surface 1, this is surface 2. When they are contact, there is maybe some irregularities. There cannot be perfect contact. So some air may leak. Here air may leak. That may be very small, but that will offer some resistance. This is the temperature fall due to at the contact between the two surfaces. Supposing no contact resistance means temperature fall will be continuous. Here no contact resistance, then the temperature drop will be like this, temperature change having a different conductivity K1, K2. Heat transfer is in this direction. If there is a contact resistance, there is a temperature fall little. But generally we don't consider in drawing the thermal circuit, we will never consider the contact resistance. So I can say as a result of contact resistance at the contact between walls, total thermal resistance against heat flow will increase. Hence, heat transfer rate decrease. So, this is the effect. Due to this contact resistance, temperature fall, no, the total resistance against the heat flow will increase the heat. Now, in this case, if you compare here and here, same slabs, everything same. Here you will have the heat transfer rate more, Q more here. Here Q will be lesser. Everything else same. If it's suppose same material, same thickness, same temperature difference, if you think, here you have got this extra resistance. That is why heat transfer rate will slightly decrease, not much, but it will slightly decrease. Contact resistance happen due to the imperfect contact between the surfaces. Because some aberrations will be there on the surface, there will be aberrations. When you are pressing the materials, there may not be complete contact, perfect solid to solid contact. Some gap may be there, tiny gap, into that air may leak and that will offer the resistance. Air is a very bad conductor of heat. Air is a very bad conductor of heat, 0.026 its conductivity. Air is a very, very bad heat conductor. These are all the convection problems, that is. Yes. What is critical radius of insulation? It is the radius of insulation at which the heat transfer rate from the cable or thin wire to atmosphere is maximum. What is the, if we want to see the importance, this is the importance. If the radius of the wire initially considered, this is the, from the graph only we can always explain this. This is, if this is the critical radius of insulation given by K by H, if the radius of the wire considered is lesser than the critical radius of insulation, if the radius of the wire, if the radius of wire initially considered is lesser than critical radius of insulation, like this in the left hand side domain, in this domain I am talking in this domain. If the radius of the wire initially considered is lesser than the critical radius of insulation, any insulation added to it will result in increase of heat transfer rate. You can see clearly in the figure. Suppose if the critical radius calculated is 10 mm, but I have considered a radius of 5 mm, that means you are beginning the journey here. That means if you add the insulation, you are moving in the right side, heat transfer rate will increase instead of decreasing. If the critical radius of the insulation is 10 mm, K by H value, if you consider a wire of radius just 5 mm, which is less than 10, somewhere here, if this is 10, you consider a wire of radius 5 mm, cable or a wire, and you have put up some insulation around it, heat transfer rate will increase instead of decreasing. But that will continue till you reach the maximum heat transfer rate, till you get the maximum where the radius of insulation is critical, given by K by H. After that, this increase will continue up to critical radius of insulation. This increase will continue up to critical radius of insulation, beyond which any insulation added will decrease the heat transfer rate, beyond which any insulation added will decrease the heat transfer rate again as such. So, critical radius of insulation is the radius of insulation provided where the heat transfer rate from the cable to the ambient is maximum. Okay. You have got a wire, you are putting the insulation, keep on changing the, putting more and more insulation. At that critical radius of insulation, you will see the maximum rate of heat transfer between the cable and the surroundings. If this is a cable, if you put the insulation around it, at the critical radius of insulation, if you put up this critical radius, the heat transfer rate from the cable to the ambient will be maximum. That is the significance of the critical radius. Actually, where practically it is used? Practically it is used in the domestic electrical cables. In the domestic electric cables, you wantedly add the insulation not to decrease the heat transfer rate, rather to increase the heat transfer rate. Right, you see, you are in the domestic electric power transmission cables, in the household electric power transmission cables, you are putting the insulation not to decrease the heat transfer rate, rather to increase the heat transfer rate. There, that is a practical application of critical radius of insulation. Best example is domestic electric power transmission cables. Insulation is put up to increase the heat transfer rate. Why you have to increase the heat transfer rate? Because when the current is passing in the cable, heat is generated. That heat must be taken off quickly. When electric power is transmitted through the cable, heat is generated. That heat must be quickly dissipated, taken off. For that they are putting the insulation, not to decrease the heat transfer rate, rather to increase the heat transfer rate, insulation is kept. Explain lumped system analysis. Very good, important question. Unsteady state. Now we are talking about most important topic in conduction, unsteady state heat conduction or transient. Suppose that there is a furnace. Inside a furnace, a body is sufficiently heated. The body is sufficiently heated to initial temperature inside a furnace, maybe 200 or 200 degrees Celsius, suddenly taken out of the furnace and exposed to the ambient fluid at T infinity. Okay. The body is heated and suddenly taken out of the furnace and exposed to the ambient fluid at T infinity. The moment it is exposed to the ambient fluid, it keeps losing heat by convection with a convection heat transfer coefficient of H, and as a result the temperature of that body keeps on decreasing. Temperature of the body becomes a function of time. This is called as the transient heat conduction. Temperature becomes a function of the time. Now at the moment you take it out of the furnace, its temperature is initial temperature Ti. Initial temperature of body when taken out of furnace. When taken out of furnace, that is at time tau is equal to 0. The moment it is taken out of the furnace, you put on the stopwatch. So at that instant of time, this is the initial temperature, right? Now as the time passes, as the stopwatch keeps on ticking, temperature keeps on decreasing. That is, temperature becomes a function of time. Now we have to develop that function, temperature versus time, so that at any instant of time, at any instant of tau, I can calculate the temperature of the body by using that lumped heat capacity analysis. I will do that analysis after the break. Let us go for the lunch break. After the break, I will do that analysis where I define very important number called as the Biot number. Hello students, welcome back to the class. This is Sekhar from Msigma Gokulam, and now I have been discussing about this unsteady state heat conduction, which is also called as the transient heat conduction. What is the meaning of this transient heat conduction or unsteady state? The temperature at a particular location inside the body keeps changing with respect to that time. In the steady state, the temperature at any particular location within the body will not change with time. The main difference you should understand between the steady state and the unsteady or transient, both mean the same. If the temperature at any particular location within the body, if it is changing with the time, it is called unsteady. If it is not changing with time, it is called steady. Most of the heat transfer problems come under the steady state category. Unsteady state are there, but not that much common as compared to the when you see the exams there. But the unsteady state also is very important topic, which is generally asked in the conduction chapter, unsteady state conduction. Here what I have considered is, I have taken a body heated inside a furnace to a sufficiently high temperature, initial temperature of the body. I had already given initial temperature of the body when just taken out of the furnace at a time tau is equal to 0 second. So that means I have heated a body inside a furnace, suddenly taken out of the furnace. At that moment, instant of time, when I take the body outside the furnace, I put on the stopwatch. So the moment it is taken out, I put on the stopwatch. That means when the stopwatch time is tau is equal to 0 seconds, the body is showing a temperature of, body is having a temperature of Ti, I for initial. At that instant it is taken out. The moment it is taken out and exposed to the air, or maybe you may drop that body in a oil bath or a water bath. You must have done in the metallurgical operations, quenching, annealing, they are all do this metallurgical treatment, heat treatment of the metals as such to change the microstructure and to change the mechanical properties, right? So you can think of in the similar manner. The moment it is taken out of the furnace, because of there is a lot of temperature difference is there, Ti is more than the T infinity, the body keeps losing heat by convection with a convection heat transfer coefficient of H. So the temperature of the body keeps on decreasing as the time progresses. After a sufficiently long time, I had given enough amount of time for the body, lot of time, given enormous amount of time, finally the body may approach or reach even the temperature of the ambient. But that takes a lot of time to approach or to almost to reach the ambient temperature. It may take a lot of time. Of course, that depends on the material properties, etc., and what is the fluid there and what is the convection coefficient. There are many parameters will decide how much time it may take, for the body to almost reach the temperature of the ambient. Fine, okay. So now my problem now is how to establish the temperature versus time. That is called as the lumped system analysis. So let T is equal to temperature of body at any instant of time tau seconds. When tau is equal to 0 seconds, temperature of the body is Ti. T is the temperature of the body at any instant of time tau seconds. Now I write the energy balance equation. Writing the energy balance equation for the body at any instant of time tau seconds at any instant of time tau seconds. If you just write the energy balance equation, see, at some instant of time during the cooling of the body, if the rate of heat transfer between the body and the fluid is 100 watts. Say for example, at any instant of time, the rate of heat transfer between the body and the fluid is 100 watts. That means body is losing 100 joules of heat in 1 second. Because of that heat loss of 100 joules in 1 second,
the internal energy of the body must exactly decrease by 100 joules during that 1 second. At any instant of time, if the rate of heat transfer between the body and the fluid is say 100 watts, that means body is losing 100 joules of heat in 1 second. 1 watt is 1 joule per second, right? 100 watt means 100 joules per second. In 1 second, body is losing a heat of 100 joules to the fluid. Because of that heat loss, the internal energy of the body must exactly drop down by 100 joules during that one particular 1 second. So, the rate of heat transfer between the body and the fluid at any instant of time must be equal to the rate of decrease of internal energy of the body with respect to the time. The rate of heat transfer between body and fluid at any instant of time, thou seconds, is equal to the rate of decrease of internal energy of body with respect to time. What is the rate of heat transfer according to the Newton's law of cooling? HA delta T. T is the temperature of the body at that instant of time, thou seconds, because of which its internal energy is decreasing by dt by d tau. Tau is the time here. Mind that tau is the symbol I am using for the time, where m is equal to mass of the body. M is the mass of the body, Cp is its specific heat, V is the volume, rho is the density. Standard things, rho is standard symbols. Rho is the density, V is the volume, Cp is the specific heat, joule per kg Kelvin, and m is the mass. Okay, so many joule per second or watts. But mass is density into volume, rho V Cp dt by d tau joule per second. Now, in this, that means the rate of heat, why I am writing minus actually, you may ask. As the time is increasing, the temperature of the body is decreasing, right? As the time is increasing, temperature is decreasing. That is why this minus has been written. So, in this equation where A is the surface area of the body, contact area, because in the convection Newton's law of cooling, A is the contact area between the body and the fluid. In this equation, there are many parameters that are constant. H is constant, A constant, A is a surface area constant, T infinity ambient temperature is constant, density constant, volume constant, specific heat is a property which is a constant. Only two variables, time and temperature, just only two variables are there. So, I will separate the variables. Separating the variables, time, tau and temperature T. Now, if you just separate the variables, time on one and temperature T. If you just look at this and see dt by T minus T infinite on one side, remaining all things are the other side. HA by rho V Cp into d tau is equal to minus d by dt by T minus T infinity. Now, we could integrate this. What are the, put the limits there to avoid the constant of integration. If you put the limits, you can avoid the constant of integration. What are the limits for tau? Tau is equal to 0 seconds. At that instant, Ti is the temperature. Tau is the temperature, T is the time at any instant. At that instant, T is the temperature of the body. All this is a constant I already mentioned. HA by rho V Cp is a constant because everything is a constant there, into tau is equal to ln T minus T infinity by t minus t infinity between the limits, interchange the limits, they remove the minus and interchange the limits ti minus t. Okay. Now it becomes log ti minus t, log a minus log b is log a by b. Okay. Remove the minus and interchange the limits. So now this is a base e, implies it becomes e to the power of HA by rho VCP into tau is equal to Ti minus T infinity by T minus T infinity. So this is the function meant for calculating the temperature of the body at any instant of time tau. Knowing that tau, I can get the temperature and vice versa. Knowing the temperature, I can calculate the tau, or knowing the tau, I can calculate the temperature. Right? That means I can say the temperature of the body decreases exponentially with respect to the time, or changes exponentially, may increase sometimes also. That is, the temperature of body decreases or changes rather, sorry, the temperature of body changes, may increase or decrease, changes exponentially with respect to time during transient or unsteady state conduction, particularly in this lumped heat analysis. What is the meaning of this lumped heat during unsteady or unsteady state heat transfer? In all these examples, in this entire example, in this all this analysis, we have made one hidden assumption, one underlying assumption that, one hidden assumption that temperature of the body is uniform throughout its mass at any instant of time. In this entire analysis, I have made an assumption that the temperature of the body at every location is same. Temperature is changing with time, but at any instant of time, if you observe the temperature of the body inside at the core of the body or at the periphery, it is same. At the core of the body, that means supposing this is a body, at the periphery, at the core, at this location, at every location we are observing the same, we are assuming the same temperature. Body is losing heat by convection, but the temperature at every location we are seeing the same temperature here, 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 at the core of the body, periphery of the body. Okay. So that kind of analysis is called as the lumped heat capacity analysis. This is the meaning that in the above analysis, it is assumed that the temperature of the body is uniform throughout its mass at any instant of time. The temperature of the body is uniform throughout its mass. That such analysis, that means temperature is only a function of time, but temperature is not a function of space or location within the body. That such analysis is called, you may write one, that is internal temperature gradients within the body are negligibly small. There may be gradients. Supposing here it may be 100, here it may be around 99.999. So the difference between them is almost zero. Between any two locations, the temperature difference. Such kind of things is called as such analysis is called as lumped heat analysis. Is called as when can you write this? Actually, is there any criteria? Somebody asked, can you write all the cases of unsteady state this analysis? No, no, we can't write. There is one important criteria is there, important condition is there. That condition is that Biot number. That condition is given in the form of a Biot number, which is a dimensionless number. Very important. The only one dimensionless number. Of course, there is one more is also there called as a Fourier number. This is the main actually. In conduction chapter is Biot number. Another number is also there, Fourier number, but that will be applicable for the analysis where lumped heat analysis is not there, not possible. I will give you that situation also. Criteria, when you can write this lumped heat analysis, I am giving the criteria. This is the criteria. Biot number should be less than or equal to 0.1, where Biot number is equal to Hs by, many exams it may ask this Biot number. S is the characteristic dimension of body which is given as volume of body divided by surface area. V by A. For spherical body, S will be R by 3. Where is for spherical body, R is the radius of the sphere. So as long as the Biot number is less than 0.1, less than or equal to 0.1, we can feel free to write the Biot number. Biot number, we can feel free to write the earlier formula, that is lumped heat analysis formula, that is this formula. This formula is valid whenever there is a lumped heat analysis is applicable. Okay, and I am giving the Biot number definition also. I am giving the definition of Biot number. It can be written as S by Ka. K is the conductivity of the solid there, divided by 1 upon Ha. Same, that will result in this Hs by K. So this would be, it is numerator resembling the something like a conduction thermal resistance, and the denominator is resembling the convection thermal resistance. So the numerator is a conduction resistance, denominator is a convection resistance. So I am writing the definition like this: internal conductive resistance offered by body divided by external convective resistance that is prevailing at the surface. Actually, in this analysis, in this case, what in the entire analysis I have done, there are two modes of heat transfers are happening. What is happening at the periphery surface is convection mode, but internally there is something else is happening. Internally there is something else is happening. What is that? Conduction. Internally there is something happening, this conduction within the, supposing if the surface is getting cooled and this periphery temperature is decreasing, immediately the body senses the temperature difference, rapidly supplies the heat. If this conduction is happening very, very rapidly as compared to this convection, then lumped heat analysis is valid. That means this internal conduction is happening very fast as compared to the surface convection. Then lumped heat analysis will be valid. We do not see any internal temperature gradients. So, for that, what is the condition? The body must be thin, the body must be a small spherical body or a thin plates, slender rods. For all these cases, lumped heat analysis made up of a good conducting. Look at this. Look at this value definition of the Biot number. Biot number should be less than 0.1. For that, K must be high or S must be small. Then only Biot number, small Biot number values, right? S must be high. That means S must be S must be small, K must be high. For S must be small, it should be of a small radius ball or a slender rod or a thin plate. You can feel free to write the lumped heat analysis. That is lumped heat analysis is practically valid if body is of small size, like small spheres, thin plates must be thin plates, slender rods. Slender rods means long rod but of small diameter. It is like diameter is small but the length is more. For all these cases, practically lumped heat analysis is practically valid if body is of small size and made up of good thermal conducting material like a steel, like that, good conducting material. Any metal, for that matter, any metal is a good conductor. Any metal is a good conductor of heat. A metallic body but slender shaped body, thin shaped body, automatically Biot number will be automatically less than 0.1, 0.1. Okay. So, this is of importance of the, supposing if Biot number is more than 0.1, in case if Biot number is greater than 0.1, maybe 0.5 or 0.7 like that, then Heisler charts are required to be used to solve the problem. Lumped heat analysis is not valid. Heisler charts are required to be used. I will show you the typical way of Heisler charts there. I will show you the Heisler chart for infinitely long cylinder. Infinitely long cylinder of radius or infinitely long cylinder for central line temperature or axis temperature. This is the typical Heisler charts for a x-axis is Fourier number. We got two numbers here in this F4. That is, formula is alpha tau by RO square. Like that, these are the So, these curves are this is the reciprocal of the Biot number. Each line is for the reciprocal of the Biot number. K by HRO. Characteristic dimension here is RO only. RO is the radius of the rod, K is the thermal conductivity, T infinity is the ambient fluid temperature, Ti is the initial temperature, Ti is the initial temperature. TO is the axis temperature. How the axis temperature vary with time? At any instant of time tau, I can calculate the center line temperature there. Ti is the initial temperature, T infinity is the ambient temperature. This is the for the cylindrical, infinitely long cylindrical rod. This is a typical Heisler chart. Supposing you have taken an infinitely long cylinder. You have heated in a furnace, suddenly exposed to the ambient fluid. Lumped heat analysis is not valid. That means Biot number is greater than 0.1, 0.5 or something like that. Say after 1 minute, say for example after 1 minute, what is the center line temperature I want to calculate at the axis? What I do, I know the time is equal to 1 minute 60 seconds, alpha is equal to K by rho Cp, that material thermophysical property. What is that? Thermal diffusivity. Alpha is called thermal diffusivity, and RO is the radius of these. I can calculate Fourier number. I know the K by HRO. H is also given, convection coefficient. H is also given. I can calculate K, because K is the conductivity of the solid. I know this Biot number I can calculate. From the Fourier number and Biot number, reciprocal of the Biot number here, these lines, I can get this value. Once I get this value, I know the T infinity, I know the initial temperature of the rod at which it is exposed, suddenly exposed. Ambient fluid temperature I know, okay. I can calculate the center line temperature. Say after 1 minute, if you want to calculate the TO, just put this alpha, calculate alpha, tau is equal to 60 seconds, RO I know, radius of the cylindrical rod, infinitely long cylindrical rod. Get the Fourier number and intersect the Biot number and come this way. And once you get this value, I can calculate the axis temperature at that instant of time. Heisler charts are very useful, particularly when the lumped heat analysis is not valid. Now that Biot number is but the Biot number is greater than 0.1. If it is less than 0.1, we don't have to come to this chart. If the Biot number is less than 0.1, we don't have to use the Heisler charts. Directly we can use the earlier formula I have derived for the lumped heat analysis. Earlier formula, exponential function which I have derived, that is valid for the lumped heat analysis. That is, feel free to use that equation as long as Biot number is less than 0.1. If it is Biot number is greater than 0.1, we have to use the Heisler charts to calculate the temperature at any particular location within a body. Similar charts are available. Separate chart will be there for a sphere. For a spherical, separate chart. For a thin plate, separate chart will be there. Actually, Fourier number definition also somebody will ask actually. The rate of conduction heat transfer, within body divided by rate of energy storage, rate of heat energy storage. That is also called as Fourier number, the Fourier number definition. This is the definition of the Fourier number you can think of. Right. Okay. Now, having seen this, having seen the important cases of conduction, now you should be able to calculate for any, for example, for a composite cylinder, if you want to calculate, for a composite cylinder thermal circuit, there is a hollow cylinder, this is the axis, this is inner cylinder, this is the outer cylinder, L is the length of the cylinder and K1 is the conductivity here. Supposing if this is a hot gases are there at a Tg, this is the colder ambient at T infinity. So, what is this mode of heat transfer here between the hot gases here? Convection. Convection means immediately we have to be given the H1, watt per meter square Kelvin. This is a conduction. K indicates conduction, just like H indicates convection. There is again convection happening from the outer surface with H2. With H2 watt per meter square Kelvin, that is L is the length, R1, R2, R3 are the dimensions there. So, totally there are 4 resistances between Tg and T infinity. This is the direction of the heat, radial heat transfer. This is the direction of the radial heat transfer, this way. This is the direction of the radial heat transfer, first by convection, conduction and again by convection. So, the thermal circuit has steady state, assume steady state heat transfer, assume steady state one dimensional radial heat transfer, totally how many resistances will be there? 4. Convection, conduction and again convection. So, the thermal circuit will have, the thermal circuit is the main core of the problem. In any conduction convection problem, particularly first chapter, in any particular, please draw the thermal circuit whether he has asked or not. In any problem wherever you are attempting the conduction problem, first chapter, a composite slab or composite cylinder like this or critical radius, whatever it is, wherever the problem there, except fin we do not draw, heat generation also we do not draw the thermal circuit. We should not draw the heat generation case thermal circuit. So, all other cases we have to draw the thermal circuit. There are 4 resistances. This is Tg, this is T infinity. First thing is the convection inside. Then we have the conduction here. Then of course conduction is there. And finally outside convection. First resistance will be, convection resistance is always given by 1 by HA. Convection resistance is always given by 1 upon HA. What is that A? area of contact, area of touch between the body and the fluid. What is the area of contact inside? Look at this. What is the area of contact? 2 pi r1 into L. Then we have ln r2 by r1 divided by 2 pi k1L, conduction resistance. Then we have ln r3 by r2 divided by 2 pi k2L. Then we have 1 upon h2 2 pi r3L. This is the, so there are three temperatures we can mark. The terminals there, three temperatures there of the surfaces, we can mark it here. So, Q is equal to rate of heat transfer is equal to Tg minus T infinity sigma RTH, sigma RTH, thermal sum of all the thermal resistances. Okay. From once you get the heat current, we can calculate the temperature, any temperature T1, T2 or T3. Once you know calculate the heat current there. So this is how this the problem must be solved in the regarding the composite cylinder or a composite slab. Sometimes the problem may come regarding the heat generation cases. Heat generation cases are also very important. I will consider one heat generation case. I will try to solve. Heat generation in a slab. Suppose that there is a slab, heat is being generated uniformly. In the earlier case, in the earlier cases whatever we have discussed, there was no heat generation inside the body. There was no heat generation inside the body. Now there is a heat generation. Throughout the body there is a heat generation. There is a fluid here, both sides fluid is there. And this is the center line of the body. This x coordinate, 2L is the thickness of the slab, A is the area of the slab, Q dot is the rate of heat generation. This Q dot is always symbol I use for the rate of heat generation per unit volume. Per unit volume. Now my object here x is equal to 0. If you take the coordinate, x is equal to plus L, here x is equal to minus L. Okay. So this is my objective of this analysis, entire analysis is there is a heat generation inside a slab. Throughout the slab there is a uniform heat generation. My objective of the analysis is to get what is this function. How do the temperature vary inside the slab? If I get this function, I can calculate the temperature at any location as such, right? Objective assumption, assume steady state heat transfer condition. Temperature is not a function of time. That is the meaning of steady state. You are generating heat inside the body, everywhere, not a single point generation. Here, at every location, inside the slab there is heat generation. But the temperature of the slab is not changing with time. How is it possible? You are generating heat inside a body. Your generation means some other form of energy, maybe electrical or a chemical or nuclear, some other form of energy is getting transformed into heat. But the temperature of the body is not changing because you are assuming steady state. How is it possible? This can be possible if whatever the heat generated in the entire slab is given out in the form of convection. Convection heat loss to the fluid. Yes, that time then we can assume that if all the heat generated in the slab is completely given out in the form of convection to fluid, supposing 100 watts you are generating, 100 joules of heat is generated in 1 second. In the same second, if heat transfer is happening by 100 joules per second to the fluid, yes, we can maintain this steady state. Number 2, one-dimensional heat conduction. T is a function of x only, and uniform heat generation. Q dot is constant. At every location you are generating the same amount of heat. At every location you are generating the same amount of heat, not that you are generating more heat here, you are generating lesser heat here, not like that. Throughout the slab, where at every corner, at every point, we are generating the same amount of heat. That is called uniform heat generation, which means Q dot is not a function of x. So, this problem can be solved by considering that generalized heat conduction equation, because that is the case which is valid for all the situations of conduction. Right? This is the generalized conduction equation in Cartesian system. Of course, because we are assuming a one-dimensional conduction, these two will become 0, and this is the steady state. We said steady state means dou T by dou tau is also 0. So, you are left with only 2 terms. You are left with only 2 terms there. So, this is the, by integrating this we can get that. Now, we can get the d square T by dx square is minus q dot by k. Integrating dt by dx is minus q dot by k into x. First time I am writing the constant of integration C1. Why? When you write the constant of integration, you don't have any limits of integration, we have to write the constant of integration. Again integrating, q dot is constant, k is constant. K is the thermal conductivity of the material of this slab. Okay. C1 and C2 are constants of integration that are to be obtained from boundary conditions. That are to be obtained from boundary. You will be giving the problem, what is the boundary condition? What is the boundary condition means? At x is equal to plus L, what is the temperature? At x is equal to minus L, what is the temperature? You will give two. If you know the two boundary conditions, we can get the two constants of integration. Now you can calculate the temperature at any particular point. Okay. But one special boundary condition I am proposing. I am proposing one special boundary condition. one special boundary condition is that at x is equal to plus L and x is equal to minus L, temperature is TW. Both sides of the slab are at the same temperature. When it will be possible, actually practically thinking, when it will be possible, you are generating heat. You are generating heat in the slab, but right side and left side I want to see the same temperature. When that will be possible? This can be possible only if both sides the fluid must be same and both sides the fluid temperature also must be the same, okay, and you must have the same convection coefficient on both sides. You must have the same convection coefficient. Then only same fluid temperature, same fluid should be there, same fluid temperature should be there, same convection heat transfer coefficient should be there. Then you may think of that TW is same on both sides. Supposing one side water, other side air, you will not see the same temperature. Water side you will see the lesser, air side you will see the more. One side air, other side air, but one side air is moving, windy, air is blowing there. Other side still air. Still air side you will see the more temperatures than on the moving air side. So that means you should have the same fluid at the same temperature with the same convection coefficient. There are many things that will decide this particular boundary condition. But for time being, I am assuming that both sides the temperatures are same. To satisfy this boundary condition, C1 must be 0. To satisfy this boundary condition, this should not be there. C1 should be 0. Please note that C1 will be 0 only if both sides of the same slab are at the same temperature. In case if both sides of the slab are at different temperatures, then C1 will not be 0. Mind that. In case if both sides of the slab are at different temperatures, C1 would not be and cannot be 0. It will be non-zero. Mind that. Okay. The temperature of slab is maximum T is a continuous function of x when dt by dx is equal to 0. That means this is a 0, right? Dt by dx is 0. C1 we have already made 0. We think that both sides of the slab are at the same temperature. That means x has to be 0, is not? Implies x should be equal to the 0. Look at this. Dt by dx 0 means C1 is already gone because you are proposing that both sides of the slab are at the same temperature. X0 means what? X0 means what? Here at the mid plane. At the mid plane you will see the maximum temperature. That is at x is equal to 0, that is at the mid plane, we see maximum temperature of slab. Let the maximum temperature of slab be T0. I am proposing that maximum temperature of the slab is T0. At x is equal to 0, T is equal to T0. If we substitute that boundary condition here, C1 is already gone, implies T0 is equal to C2. We got both the constants of integration. Therefore, temperature is equal to minus q dot by k into x square by 2 plus T naught. This is the temperature distribution inside the slab. What kind of distribution is that? It is the parabolic temperature distribution. It is the parabolic with maximum temperature at the center line. Both sides same temperature, but maximum temperature. Then only we will see the maximum temperature at the center. This is the parabola, parabolic temperature. Whenever there is a uniform heat generation, you will get the parabolic temperature distribution. Okay. X is equal to 0 at the midplane. If you put at x is equal to plus L or minus L, T is equal to TW. If you substitute there in this, T naught minus TW is equal to Q dot L square by 2K. This is L. Only half of that. Half of that thickness is L. At x is equal to plus L or minus L, okay, L is the half of the thickness of the slab. Parabolic temperature distribution. That is true. Actually, whenever there is a heat generation is there, you can write that kind of a boundary condition. Even for cylinder, supposing, say for example, if you want to calculate the TW, say for example, to calculate TW, you want to calculate the TW. Total heat generated, energy balance this. Energy balance to calculate the center line time, to calculate the sidewall temperature, energy balance for steady state. If you write the energy balance for steady state, what is the meaning of steady state? You are generating heat in the slab, but you want to maintain the steady state. That means all the heat generated should be convected from left hand side and right hand side, right? And what is the fluid temperature here? T infinity. Here also the fluid temperature is T infinity, right? There is a convection here, there is a convection. That means for steady state, whatever the total heat generated in the slab, whatever the total heat generated in the entire slab must be convected from both sides. Then only steady state can be maintained. I already said, whenever there is a heat generation in any body, if you want to maintain the steady state means what? Temperature at a particular location must not change with respect to the time. To maintain the steady state, whatever the heat generated in the entire body must be convected off from its surface. What is the total heat generated? Q dot is the heat generated per unit volume. What is the volume of the slab? A into 2L. Q dot into A into 2L is the rate of heat generated. It should be equal to the right side convection heat transfer plus left side convection heat transfer. To calculate TW, total heat generated in slab is equal to total heat convected from both sides of the slab. What is the total heat generated? Q dot into A into 2L into 2 both sides, right. So, you will get the T dot A gets cancelled, 2 also gets cancelled, Q dot TW is equal to Q dot L by H plus T infinity. This is the side wall temperature, which is same on both sides. Side wall temperature same on both sides. So, now I can, you know how to calculate the TW, we know how to calculate the TW, this is, we know how to, because once you get the TW here, we can calculate the T naught also. Once you know this, I know the L, I know the K, I know Q dot, I can calculate T naught also. What is the T naught? Maximum temperature which you are observing at the mid plane. You will see the maximum temperature at the mid plane of the slab only when both sides of the slab are at the same temperature. Remember that. What are the 3 modes of heat transfer? They are explained already: conduction, convection and radiation. We have to give the examples and write them. Now, having seen this, now I will pick up the easier chapter, which is of easy to solve in the in the entire heat transfer subject. That chapter will be the easiest chapter, I can say. That chapter is called heat exchangers. Because in the heat exchangers there are only 2 types, actually 3 are there, but mainly they will ask about the 2. 3 are there: parallel flow, counter flow and cross flow. But usually they will ask about either parallel or counter. Only 2 heat exchangers are there, only 2 methods of problem solving are there. 2 methods of problem solving. One is LMTD method, log mean temperature difference method. Other thing is the effectiveness NTU method. Only 2 methods are there. Any problem of heat exchanger can have to be solved only by those 2 methods. What is actually a heat exchanger? Heat exchanger is a device in which 2 flowing fluids exchange or transfer heat between them due to temperature difference by conduction, convection and also maybe by radiation. All 3 modes may be there sometimes, but usually we consider conduction, convection. And as a result, that the temperature of the hotter fluid decreases and the temperature of the cold fluid will increase. Heat exchanger is an adiabatic device in which 2 flowing fluids exchange or transfer heat between them without losing any heat to the ambient. This is a heat exchanger. A hot fluid will be passing, there may be a cold fluid may be passing. This is a hot fluid, this is a cold fluid. This is the hot fluid. I said fluid. When I say fluid, that could be anything, maybe oil, gas, vapor, steam, flue gases, or a water, oil, any option is open. Oils or water or a air or a gas or a combustion gases, anything. But there must be under fluid. They are running. They are not stagnant. They keep flowing. Because they keep flowing, they must have the mass flow rate. M dot H, M dot C. Standard notation: hot fluid inlet, hot fluid exit, cold fluid inlet, cold fluid exit. Okay, it is a heat exchanger is an adiabatic device without any external work done. Okay, is an adiabatic device. It is an adiabatic in which two flowing fluids exchange or transfer heat between them without losing any heat. If mass flow rate is not given, we can use the continuity equation. V is the velocity. Mass flow rate of the fluid. M dot is the mass flow rate of the fluid, right? Continuity equation we can. So, only 4 temperatures, 2 mass flow rates. Now we could write the energy balance equation for this. From first law of thermodynamics or from law of conservation of energy, this equation will always be required to be used in any heat exchanger problem. From law of conservation of energy, the rate of enthalpy decrease of hot fluid is equal to the rate of enthalpy increase of cold fluid. M dot H CPH THI minus THE is equal to this equation. We have to keep it in mind, because in any problem of heat exchanger, this equation must be written. Any problem. CP are the specific heats, then because we know that CP means specific heats of fluid. H for hot fluid, C for cold fluid with standard notation. C meant for cold fluid, H meant for hot fluid, specific heat of flowing fluid. And incidentally, because in thermodynamics also I have mentioned that heat transfer in a constant pressure process is equal to change in enthalpy. This is the thermodynamic rule. Change in enthalpy of fluid. Heat transferred in a constant pressure process is equal to the change in enthalpy of the fluid from thermodynamics. So, I can say that either of these two equations must be indicating the rate of heat transfer, either this equation or this equation. Either of these two equations will indicate the rate of heat transfer between hot and cold fluids in the entire heat exchanger. Thus, because why are you saying like that? We are assuming that as the fluids are passing through the heat exchanger, their pressures are supposed to be constant. Their pressures will not change. Supposing a hot fluid is enters at 1 bar, it comes out at 1 bar pressure. If the cold fluid enters at 0.5 bar, it comes out at 0.5 bar. Pressures will not change. As they flow through the heat exchangers, pressures will not change. So, with that assumption, from thermodynamic rule, I can say that thus rate of heat transfer between hot and cold fluids in any heat exchanger is equal to, either we can write this, either the rate of enthalpy change of the hot side fluid or rate of enthalpy change of the cold side fluid. Either this or this, either of them will indicate the rate of heat transfer between hot and cold fluids, because we are assuming that hot and cold fluids are not losing any pressure, and thermodynamics say that heat transferred in a constant pressure process is equal to change in enthalpy of the fluid. From one side we are assuming that the pressure of the fluid is not changing as it passes through the heat exchanger. And from other side, thermodynamics is telling that if the pressure is constant, either heat given to the fluid or taken from the fluid is equal to change of its enthalpy. And we have already done the rate of enthalpy change of hot and cold. So either of them will indicate the rate of heat transfer Q between hot and cold fluids. This is a very striking point in the heat exchanger analysis. Whenever you are attempting a heat exchanger problem, always keep in mind that the rate of heat transfer in entire heat exchanger between hot and cold fluids is equal to either the rate of enthalpy change of the hot side fluid or the rate of enthalpy change of the cold side fluid. The rate of heat transfer between hot and cold in entire heat exchanger is equal to either the rate of enthalpy decrease of the hot side fluid or the rate of enthalpy increase of the cold side fluid, given by these two formulae which are given, m dot h Cph Thi minus Dh. So that point you please keep in mind whenever you are solving the heat exchanger problem. Okay. But keep the specific heats in joules there, so that you get the rate of heat transfer always in watts. Right. Now, having seen the general analysis of heat exchanger, now we will have the classification, right? Classification of heat exchangers. If you see, we will have the parallel flow and contour flow. I will draw the temperature profiles also here. You in the exam also we have to mention the temperature profiles. This is the parallel flow heat exchanger, because hot fluid and cold fluid are flowing parallel. This is the, why it is called parallel flow, because both the fluids are commuting in the same, both are flowing in the same direction. This is Thi, this is The, this is Tci, I have given the temperature profiles also. This need to be drawn in every heat exchanger problem in the exam. We have to draw this temperature because they carry the marks. This one, these are the, this is for the hot fluid temperature profile, this is for the cold fluid. Then coming to the, this is the counter flow heat exchanger. This is what we have drawn is the parallel flow. Now I am drawing the counter flow. Counter flow means both are traveling in the opposite direction. Both the fluids are commuting in the opposite direction. Now notations are standard. Th for hot, C for cold, I for inlet, E for exit. Exit means going out, right? Exit temperature. Now this is the this is the counterflow heat exchanger. Both are commuting in the opposite direction. THI, THE, TCI, this is the temperature profiles of the counterflow heat exchanger. One has to draw these temperature profiles in every heat exchanger problem. Please keep the arrows. This is hot fluid, this is for the cold fluid. Okay? This is for the parallel flow, this is for the counterflow. Temperature profiles, these are, we have to draw them in every heat exchanger problem. Now, because the temperature difference between hot and cold fluids, delta D, hot and cold fluids are exchanging heat. What is delta T? The driving potential for the heat transfer, right? At any location, there is some heat transfer happening. For this heat transfer, what is the temperature difference between hot and cold fluids? At that location, there is some temperature for the hot fluid. At that location, there is some temperature for the cold fluid. Similarly, there is a heat transfer happening by convection, conduction, or whatever it is. For that, what is the driving potential for any heat transfer? Temperature difference between hot and cold fluids at that location. That is TH minus TC. Okay. TH minus TC is the temperature difference between hot and cold fluids, which is the driving potential for the heat transfer. TH minus TC, right? Now, that could be written like that. dQ is the differential heat transfer rate, U delta T dA, where dA is the differential heat transfer area, dA is the differential heat transfer area, dQ is the differential heat transfer rate, U is the overall heat transfer coefficient, and delta T is the TH minus TC. Okay. dQ is the differential heat transfer area through a dQ is the differential heat transfer rate through the differential heat transfer area dA, where the temperature of the hot fluid is TH and the temperature of the cold fluid is TC. The driving potential for the heat transfer is TH minus TC, that is delta T. This is the differential heat transfer rate through a differential heat transfer area dA. But this delta T keeps changing. See, at different locations we have a different delta T, different driving potential. Here, though actually they are looking parallel, actually they are not parallel in counterflow also. The delta T is a function of X. If X is the direction of the hot fluid flow, here delta T is a function of X. In both the heat exchangers, delta T is changing, right? From location to location, the delta T is changing. What is the delta T? Temperature difference between hot and cold fluids at any location. That keeps varying from location to the location. Therefore, I need to define one mean temperature difference. Why there is a need, why there is a necessity or a need for defining that mean temperature difference? Because the delta T is changing from one location to the another location. It keeps varying that. So, that MTD later also I call it as the log mean temperature difference, known as the LMTD. any question asked in the heat exchanger, they ask about only two parameters, either LMTD or effectiveness. There is no other one to ask, either LMTD or effectiveness. One of them only they have to ask any problem or any question regarding the heat exchanger. So, why there is a need to define the LMTD is because the delta T is changing from location to the location. This is the mean temperature difference. It can be mathematically defined like this. Later I call it as the log mean temperature difference LMTD. Since delta T is a function of x, what is it x? Direction of the hot fluid flow. Delta Tm is defined as delta T is varying from location to location, from inlet to exit. Delta T is varying. This is the MTD definition, mean temperature difference. And it is also defined from the total heat transfer rate between hot and cold fluids in entire heat exchanger. Is given by UA delta Tm, where U is the overall heat transfer coefficient. It will always be given in the heat exchanger problem. Overall heat transfer coefficient. A is the total heat transfer area of heat exchanger. Simply A is the area of the heat exchanger, we can say, which we need to calculate. In the design of heat exchanger, this A only should be calculated. So now the total heat transfer rate in the heat exchanger could be calculated from two different lines. One is I had given the UA delta Tm, where delta Tm is the MTD. Now I will give the formula for how to calculate that MTD. There is what is that Q? Q is the total heat transfer rate between hot and cold fluids. Q is the total heat transfer rate in entire heat exchanger between hot and cold fluids. This can be calculated either from rate of enthalpy change of the hot side fluid or rate of enthalpy change of the cold side fluid. Okay. Total heat transfer rate in entire heat exchanger can be calculated from either of these two equations. This is the rate of enthalpy change of either hot side fluid or cold side fluid, or you can calculate from the Q is equal to UA delta Tm. What is the, how to calculate that MTD, mean temperature difference? It is also called as the MTD. Now I am going to give the formula to calculate the mean temperature difference. Now take some break, 5 minutes break. Hello students, welcome back to the class. Just now I have defined the mean temperature difference, which takes into account the variation of the temperature difference between hot and cold fluids from inlet to the exit. See, in any heat exchanger, the temperature difference, this is delta T, that is changing. Delta T is a function of X. So as you go to from one location to the another location, delta T is changing. So what is the purpose of the mean temperature difference? That variation of delta T with respect to X has been averaged. Not a simple arithmetic average, it has been integrated from inlet to the exit, that variation. Okay. What is the formula? How to calculate that mean temperature difference in terms of the inlet and exit temperatures? Now I am going to derive an equation for mean temperature difference of a parallel flow heat exchanger. I want to derive an equation for mean temperature difference of a parallel flow heat exchanger in terms of those four temperatures. It's important derivation. Generally, they will ask you in the examinations. Generally, any question that is asked in the heat exchangers, this is most commonly asked question in the university examinations. Derive an equation for LMTD of parallel flow, or derive an equation for LMTD of contour flow. Now I am going to derive an equation for mean temperature difference MTD of parallel flow heat exchanger. This is the separating wall. This is the separating wall. Most of our heat exchangers, hot and cold fluids, they do not come into contact with each other. It is a parallel flow heat exchanger. Both are traveling along the same direction. This is THI. This is hot fluid exit. TCI, cold fluid inlet. This is the cold fluid exit. These are the temperature profiles of the hot and cold fluids, TCI, TC. I have considered a differentially small heat transfer area. This is the X direction. X direction always selected in the direction of the hot fluid flow. Remember, this is the X direction. It is always hot fluid flow direction. In counter flow also it is taken like that. Here X is equal to 0. Here X is equal to L, where L is the length of the heat exchanger. I have considered a differentially small heat transfer area of length dx, This is the differential heat transfer area, right? This is the differential heat transfer area through which the differential heat transfer rate between hot and cold fluids is dq. Dx is the differential heat transfer area length. At that location, delta T is the temperature difference between hot and cold fluids. dq is the differential heat transfer rate, where Th is the temperature of the hot fluid side, Tc is the temperature of the cold fluid side. The difference is the delta T at that location. M dot H is the mass flow rates, M dot C is the mass flow rate of the cold fluid. Okay. This delta T is a function of X. As X changes, delta T is also changing. What is delta T basically? Delta T is a Th minus Tc, temperature difference between hot and cold fluids, which is a function of X. Consider differential heat transfer area dA of the heat exchanger of length dx, through which differential heat transfer rate between hot and cold fluids through which the differential heat transfer rate between hot and cold fluids is dq. Okay. Then dq is equal to u delta t dA, that dA is, I can take it as the bdx, contact area. Now, what is that B? B is the width of separating wall, some flat separating wall I have assumed, width of separating wall. Perpendicular to plane of figure. This is the separating wall. This is the separating wall perpendicular, this in this way, perpendicular to the plane of figure, that is the B dimension. Dx is the, this is dx. This is dx. B dx, dx into B, that is the differential heat transfer area dA. Okay. Also that this already differential that thermodynamic rule I have mentioned. Whenever the pressure is constant, the pressure of the hot fluid is constant, the pressure of the cold fluid is constant. Whenever pressure is constant, the heat given or heat taken is equal to change of enthalpy. Therefore, differential heat transfer rate is equal to differential change of enthalpy of the hot fluid. See, as further travel, the temperature of the hot fluid is changing by, from here to here, changing by dTH. For that travel, for this travel, the temperature of the cold fluid is changing by dTc. So, dq could be written as minus m dot h Cph dTh. Why minus? Temperature of the hot fluid is decreasing. Plus, why I am writing the plus here? Temperature of the cold fluid is increasing in the direction of x, that is why it is written. So, this is the differential amount of heat taken, this is the differential change of enthalpy of the hot fluid as it travels through a distance of dx. Now, remaining thing is only mathematical. Now, delta T is equal to Th minus Tc, which is a function of x. At x is equal to 0, delta T is equal to delta Ti is equal to Thi minus Tci. So, look at this. This is the delta Ti. This is the delta Te. At x is equal to L, delta T is equal to delta Te is equal to The minus Tc. So, this is delta Te at the exit. This is the exit in the parallel flow heat exchanger, that is the exit. The two limiting values of the two boundaries of the delta T, I got it. At inlet it is delta Ti, at the exit delta T. Fine. Now, if you differentiate that delta T is equal to Th minus Tc, right. If you differentiate both sides, dTh minus dTc. But we know already dTh and dTc from here, I substitute here dTh and dTc here. Therefore, d of delta T is equal to minus dq divided by m dot h Cph minus of plus minus m dot c Cpc. Okay, as just substituted here dTh and dTc here in. Now, d of delta T, I can take the dq common, minus dq common, 1 by m dot h Cph plus 1 by m dot c Cpc. This dq I could write it as minus u delta T bdx In this equation, all are constants. Steady flow means mass flow rates are constant, specific heats are constant, width of the separating wall constant, all you overall heat transfer. Now, if you separate the variables, only two variables are there, delta T and X. Delta T one side and X on the other side. Minus also bring it here, delta Ti to delta Te, integral U, B, all are constants here, 1 by m dot H, m dot C, CPC, dx. The x limits are x is equal to 0, x is equal to L. Now remove the minus and interchange the limits, it becomes log delta Ti by delta Te is equal to U. All other things are constants, you can take it out. UBL but B into L is the total heat transfer area. Total heat transfer area of heat exchanger. Just substitute that ln delta Ti by delta Te 1 by m dot H CPH plus 1 by m dot C CPC. Just substitute, replaced this B into L with the total contact area, right? You can see in this figure. B is the perpendicular to the plane of the figure in this direction. In the perpendicular to the L is the length. That B dimension we cannot see in this front view. B will be the perpendicular to the plane of the figure, dimension of the separating wall. Okay, see, whenever you talk about the heat transfer area, remember, I always highlight this point. Whenever heat transfer area of heat exchanger, if you want to know, just consider contact area. Just consider contact area of the one of the fluids with the separating wall, not both the fluids. Supposing a fluid is flowing in a pipe, what is the heat transfer area? Pi d into L. Suppose if there is only single pipe, if there are n tubes are there, into n. One fluid contact area with the separating wall, that is the heat transfer area. If the fluid is flowing in a pipe, pi dl. You take outside the pipe, there may be another fluid, but we don't have to consider that. Heat transfer area is contact area between one of the fluids and the separating wall. Okay. Now we have total heat transfer rate between hot and cold fluids m dot H CPH THI minus THE is equal to m dot C CPC. Now if we substitute that, it becomes 1 by m dot H means THI minus THE divided by Q plus TCE now I can combine THI minus TCI, you can combine into one, THE minus TCE, you can take the minus common. So this will become the delta TE, this will become the delta TI. Log delta TI by delta T. THI minus TCI is UA by Q, also you can take LCM. This is THI minus TCI is delta TI. Take the minus common, this difference is delta T. Q is equal to UA delta Ti minus delta Te divided by ln delta Ti by delta T. Comparing with the definition of comparing with definition of delta Tm, Q is equal to UA delta Tm. If you compare these two, implies delta Tm of parallel flow heat exchanger is delta Ti minus delta Te divided by ln natural logarithm delta Ti by delta T. This is called LMTD because it contains logarithmic function, right? LMTD of parallel flow heat exchanger. LMTD log mean, because it contains the logarithmic function, it is also known as LMTD, log mean temperature difference of parallel flow heat exchanger. Any question asked in the heat exchanger, as I said, only two things they will ask, either LMTD or effectiveness, nothing else. Effectiveness means their NTU, all put parameters will be there, effectiveness, capacity ratio, capacity rate ratio, NTU, etc. In the same way, we could derive for the counterflow also. Same way, procedure is same, but only difference is, I'll show you. LMTD of counterflow same procedure, but only one difference will be there in the derivation. Here like this. In the counterflow, both the fluids will be traveling in the opposite direction, right? In the counterflow, both the fluids will be traveling in the opposite direction. This is THI, this is THE, but cold is entering other side, at the exit section of the cold fluid, at the exit section of the cold fluid, at the exit section of the hot fluid, cold is entering. Cold is leaving at the inlet section of the hot fluid. Both are traveling in the opposite direction. This is hot, this is cold. This is here also the direction of the x is like this. Everything derivation is same, but only difference is that this is the difference. If we just take the differential heat transfer area in the x, with respect to the x, both dTh is negative, dTc is also negative. That is the only difference. This is dTh, this is dTc. Both are negative. In the direction of the x is this direction, x is equal to 0, x is equal to L. Here the main important thing what we have to notice is the definitions of delta Ti and delta Te are different. This is a very important precaution. Here delta Ti means in counterflow heat exchanger, here in counterflow, delta Ti is Thi minus Tce. Look at this difference, Thi minus Tc. Delta Te is The minus Tci. That difference we have to fix in your mind. If you don't understand, if you don't keep in mind, you will go wrong. Definitions of delta Ti and delta Te are different between parallel flow and counterflow heat exchangers. Delta Ti there is Thi minus Tci. Here delta Ti is Thi minus Tce. Please take care of that. Delta Te there is The minus Tce in parallel flow. Here The minus Tci. That point we have to notice. Also one more definition here is, if you take the differential heat transfer rate, here, both will be negative. That is the only thing, both will be negative here. Why both are negative? Here, there in parallel flow derivation I have done, one was minus, one was plus. Here, why both are negative? As x is increasing, as x is increasing, both hot fluid is decreasing temperature, cold fluid temperature is also decreasing in the direction of the x. That is why both are negative. Procedure everything same, aim everything. Finally, you will arrive at the LMTD formula also same. LMTD of the counterflow also will be delta Ti minus delta Te. Here also the formula for LMTD is same. Delta Ti by T. In parallel, for parallel flow and for counterflow, the LMTD formula is same, but the definitions of delta Ti and delta Te are different. Note that I am writing that. The definitions of delta Ti and delta Te are different between parallel flow and counterflow heat exchangers. Between parallel flow and counterflow heat exchangers, that point we have to. And here delta Te can be greater than delta Ta in counterflow, but there the chance is not there, parallel flow. Here delta Te can be greater than delta Ta. In parallel flow, delta Te is always less than delta Ti. But it does not mean though this is greater than this, the denominator also will become a negative. Minus by minus, LMTD is always positive. But this delta Te can be greater than delta Ti only in counterflow. That chance is there. I am not saying that it is always there. And then somebody may ask, what is the LMTD of the cross flow? Cross flow means what? Fluids will run in the perpendicular direction. Hot fluid in, hot fluid out, cold fluid in, cold fluid out. Here LMTD of this is called cross flow. Cross flow heat exchanger. LMTD of the cross flow heat exchanger, what we have to do is, we have to multiply LMTD of the counterflow with one correction factor. F is the correction factor. F usually will be close to 0.85 to 0.9. Usually that correction factor value. Some special cases of special cases regarding LMTD I will highlight. Case 1. If one of the fluids is undergoing phase change, like condensation of steam. Phase change means condensation of steam. Both parallel flow and counterflow would have the same LMTD. This is parallel. When steam is condensing, its temperature will not change. That is important thing. When steam is condensing, its temperature will not change, but the cooling water temperature will increase. This is counterflow. So here it does not matter what kind of heat exchanger we are going to design, whether parallel flow or counter flow, the LMTD value is same. Here LMTD of parallel flow and LMTD of counter flow heat exchangers will become equal. It does not matter what type of heat exchanger we are designing. When one of the fluids is undergoing phase change means what? Either liquid to vapor or vapor to liquid. Whenever a liquid is undergoing phase change, that fluid temperature will not change. Whenever a fluid is undergoing phase change, either from liquid to vapor or from vapor to liquid, its temperature will not change. Temperature remains constant. When the steam is condensing into the liquid, its temperature remains constant, and that temperature only we call it as the, we will name it as the saturation temperature. In thermodynamics, we will call it as the saturation temperature, which remains constant during condensation of the steam. Okay. So, if one fluid is undergoing phase change, LMTD of the parallel flow, LMTD of the counter flow will become equal. Usually, general rule is that when everything remains same, LMTD of the counter flow you will get more usually. If phase change is not there, when for the same inlet and exit temperatures and for the same mass flow rates, LMTD of the counter flow is more than the LMTD of the parallel flow. Please keep that point. When all four temperatures THI, TCI, THE, TCE, if you use it in parallel flow and counter flow, if you calculate LMTD, you will see that LMTD of the counter flow heat exchanger is more than the LMTD of the parallel flow heat exchanger. For the same, this is an important bit also, for the same inlet and exit temperatures of both hot and cold fluids, LMTD of the counter flow heat exchanger is greater than the LMTD of the parallel flow heat exchanger. Please keep that point in mind. Right. This is one important case. Another case is case 2. This is more important case. Special case 2. When both hot and cold fluids are having equal capacity rates, that is then from energy balance equation, this is the energy balance equation which we can write for any heat exchanger. These two could be cancelled off. If you rearrange the parameters, this is delta Ti. This is delta Te in counter flow. This is delta Ti in counter flow. Then LMTD of the counter flow, if you write, if you see, you will get 0 by 0, undefined, right? Then from L'Hospital's rule, LMTD of the counter flow, see, if you just substitute the Thi minus Tce is the definition of delta Ti in counterflow. Thi minus Tci is the definition of the delta Te in counterflow. So, they have become equal in counterflow heat exchanger, particularly in counterflow heat exchanger. If both hot and cold fluids are having equal capacity rates, the product of m dot Cp product of the fluid is called capacity rate. Is called capacity rate of fluid. So, this is, now remember this. So, if they are having equal capacity rates, LMTD 0 by 0 are getting from LMTD, then from L'Hospital's rule either delta Ti or delta Te. Either delta Ti or delta Te we can write. And incidentally, and this kind of a heat exchanger is called, if m dot H Cph is equal to m dot C Cpc in counterflow, such heat exchanger is called balanced counterflow heat exchanger. Such heat exchanger is called balanced counterflow heat exchanger. For such balanced counterflow heat exchanger, if you draw the temperature profiles, this hot and cold fluid, this is the only heat exchanger where you see the straight lines, parallel straight lines. This is called, either this can be taken as LMTD or this can be taken as LMTD. Both are equal, in fact. This is called, they are straight lines. They are parallel straight lines. This is one important special case what we see regarding the counterflow. Regarding the counterflow, it is called as a balanced counterflow heat exchanger when capacity rates are equal on hot side and cold side. Right. Now, I will give the procedure to design of the heat exchanger. How to find the area. Design of heat exchanger, this method is also called as LMTD method. I already mentioned only two methods are there in any, only two methods are there in any heat exchanger problem, only two methods. Entire heat exchanger problems can be solved by only two methods. One is LMTD method, other thing is the effectiveness NTU method. What is this main objective of LMTD method? To find area. To find area of heat exchanger, that is it. That is the main objective. What is area? That is the main objective of this this LMTD method. Generally, given data will be like this. Usually, given data will be both the mass flow rates of hot and cold fluids. Compulsorily, they give the m dot H and m dot C. Compulsorily, they give the m dot H and m. Mass flow rates will be definitely given. Number 2, both the specific heats. They will also be given Cph and Cpc. Number 3, only 3 temperatures among 4 temperatures among 4 temperatures like THI, TCI, THE or TC. Only one of them, only are TCE or THE. Only one of them, only one temperature may be missing. Sometimes all 4 may be given, but usually 3 will be given, 1 will be missing. Overall heat transfer coefficient. U is a compulsorily given in every heat exchanger problem. U, which will take, what are the units for that? Watt per meter square Kelvin. All these data, any one of them is missing, we cannot solve it. What to calculate finally? To find area of heat exchanger A. Getting the area is called design. Finding the area of heat exchanger is finally known as the design of the heat exchanger. We can just get the 4 steps, within 4 steps we can get the area. Solution I am giving. Step 1. Calculate 4th unknown temperature one temperature is missing, from energy balance equation. If whenever you are given the 3 temperatures, we can get the 4th temperature from energy balance equation. What is that energy balance equation? M dot H CPH THI minus THE is equal to M dot C CPC TCE minus TCI. Only one unknown, one equation, it can be calculated. That will be either THE or TCE, one need to be calculated. 3 will be given, 4th one can be calculated. Step 2. Calculate LMTD of heat exchanger. To calculate LMTD of heat exchanger, we require all the 4 temperatures, right? And you will give in the problem whether you are designing a parallel flow or a counter flow or a cross flow, what kind of heat exchanger we are going to design, you will mention in the problem. If it is a parallel flow, you just draw the profiles. If you just draw the profiles, if it is a counter flow, draw the profiles and then get the delta Ti, delta Te. Indicate the profiles clearly. In the exam, you have to indicate the profiles clearly. This is delta Ti here. This is delta Te. Just after drawing the temperature profiles, this is for the parallel flow. You will mention, you don't have to do both. You will mention whether a parallel flow need to be designed or the counter flow need to be designed. and then calculate accordingly LMTD, delta Ti minus delta Te divided by ln delta Ti by delta T, right. We calculate the LMTD. Okay. You will mention whether parallel flow to be given or a counter flow. This is counter, right? This is counter. Whether a counter to be designed or parallel to be designed, you will clearly mention in the figure. If he has given the correction factor, means we have to design the cross flow. Any correction factor mentioned in the problem means we have to design the cross flow heat exchanger. So, okay. Then now we got the LMTD also. Step 4 is the final step. Calculate area of heat exchanger from Q is equal to UA delta Tm. A is equal to Q already obtained. How to get the Q? Either the rate of enthalpy change of the hot side fluid or the rate of enthalpy change of the cold side. You can use this one or this one based on the data mentioned in the problem. Either you can use either this Q or this one or this one. One of the step will be sufficient to calculate the area of heat exchanger. Okay, this is the procedure for getting the area. Most of the LMTD methods are meant for calculating the area only. This is called design of heat exchanger. And after getting the area, supposing if he is asking the number of tubes or etc., we can use this formula, pi dl into number of tubes per pass, d is equal to diameter of each tube, L is equal to length of heat exchanger, N is equal to number of tubes per pass based on the unknowns, number of passes. Any one unknown can be calculated. Area of the heat exchanger, P is the number of passes. Diameter of the each tube is D. Any one unknown can be calculated. After getting the area, any one unknown, either the number of tubes per pass or the length of the heat exchanger or the passes, number of passes can be obtained. So, this is a very standard procedure for designing the heat exchanger, for finding the number of tubes or a diameter. But any of them they are asked, first we have to get the area. Area is the first step. After that, either the diameter or the length or only one unknown can be obtained. Number of tubes per pass or number of passes, any one of them can be calculated. I hope you understood the design of the heat exchanger. So, one module of the heat exchanger I have done, one method. Now, I am introducing the second method called as the effectiveness NTU method. NTU, number of transfer units. How to define the effectiveness of the heat exchanger? It is the ratio between effectiveness of the heat exchanger is defined as the ratio between actual heat transfer rate between hot and cold fluids and the maximum possible heat transfer rate. And the maximum possible heat transfer rate between them. This is the definition of the effectiveness of the heat exchanger. Effectiveness of the heat exchanger is Q actually. What is the actual heat transfer rate? That we know how to calculate. How to calculate the actual heat transfer rate? That we already know how to calculate the actual heat transfer rate in any heat exchanger. The rate of enthalpy change of the hot side fluid or the rate of enthalpy change of the cold side fluid. Either the rate of enthalpy change of the hot side fluid or the rate of enthalpy change of the cold side fluid is the actual heat transfer rate. Then what is this maximum possible heat transfer rate? This should be calculated like this. In any heat exchanger, there are 4 temperatures: THI, TCI, THE, TC. Among the 4 temperatures, what is the highest temperature? THI. What is the lowest temperature? TCI. Because cold fluid has not yet received any heat, lowest temperatures among the 4 is TCI. Highest among the 4 temperatures is THA. So, between hot and cold fluids, what is the highest temperature difference existing in the heat exchanger? THI minus TCI. That multiplied by, this is the maximum temperature difference existing between hot and cold fluids, into m dot Cp small, where m dot Cp small is the smaller capacity rate between, we have 2 fluids, right? Which one is smaller? M dot, whether m dot H Cph is smaller or m dot C Cpc is smaller. Which one is smaller? That one you have to keep it here. The smaller value of these two, m dot H Cph or the m dot C Cpc, that should be multiplied with the maximum temperature difference existing between hot and cold fluids. This is the definition of the effectiveness. Please remember this, very important definition. Okay, the smaller value between m dot H Cph and m dot C Cpc should be multiplied by THI minus TCI. That is the maximum possible heat transfer rate between hot and cold fluids. In some heat exchangers, hot side fluid capacity rate may be smaller. In some other heat exchangers, cold side capacity rate may be smaller. So, now I'll take both the options. Sometimes some heat exchangers, m dot C, m dot H Cph may be smaller. Under that condition, what is the formula for effectiveness? In some other heat exchangers, m dot C Cpc may be smaller. Under that condition, what is the effectiveness? I will give both the options now. In case if m dot H Cph is smaller, is lesser than m dot C Cpc, then effectiveness of the heat exchanger will be, in the numerator, hot side fluid I take, the actual heat transfer rate, hot side enthalpy, rate of enthalpy change I take, smaller is on the hot side, right? These two will get cancelled. You will get this is the effectiveness of the heat exchanger in case m dot Cp is smaller on the hot side. On the other hand, if m dot C Cpc is smaller, then effectiveness of the heat exchanger is, numerator I will consider cold side capacity enthalpy rate. because mind that actual heat transfer rate can be calculated either this formula, or this formula, anyone, either this formula or this formula, anything can be used to calculate the actual heat transfer rate divided by, smaller is on the cold side, right? From the definition, m dot C CPC into THI minus TCI. These two will get cancelled. So, you will get TCE minus TCI divided by THI minus TCI. That means, if you want to calculate the effectiveness of the heat exchanger, first keep in mind that make sure, first confirm which side the capacity rate is smaller, whether hot side capacity rate is smaller or cold side capacity rate is smaller. Based on that, you select this formula. In case if the capacity rate is smaller on the hot side, you will get this formula. In case if the capacity rate is smaller on the cold side, you will see this formula, this one. And you can blindly remember like this, vaguely. If the hot side capacity rate is smaller, in the numerator you will get the hot fluid temperatures. If the cold side capacity rate is smaller, in the numerator you get the cold fluid temperatures. Denominator is same in both the formulae. Denominator is same in both the formulae. You may observe that. Sometimes capacity rates may be equal. M dot H CPH is equal to M dot C CPC, which you have seen, which you have already seen in the balanced counterflow heat exchanger. Under that case, any formula can be used. Otherwise, if the capacity rates are not equal, be careful to use only one of these two formulae. Only one of the above two formulae is valid at a time. Don't try to use both at the same time. Supposing if the capacity rate is smaller on the hot side, obviously it is bigger on the cold side. We can't use the second formula. If the capacity rate is smaller on the cold side, we can't use the this formula, because hot side capacity rate will be bigger then. In case, that is one special case is there. In case if both the capacity rates are equal, nothing smaller, nothing bigger, both are equal, then only any of the above two formulae can be used. Any one you can use, either this or this, for effectiveness. Only under that condition. Any of the above two formulae can be used. Otherwise, only one of them will be valid. So, whenever you are doing a problem regarding the effectiveness, first thing what we have to do is calculate both the capacity rates. Capacity rates means m dot Cp product. On hot side and cold side you calculate. Which side is smaller, put a focus on that. So, if the hot side capacity rate is smaller, in the effectiveness formula, in the numerator you get the hot fluid temperatures. If the cold side capacity rate is smaller, in the numerator you get the cold fluid temperatures. Denominator is same in both the formulae. Okay. So, this is the very important thing you have to keep in mind. Usually, practically speaking, effectiveness of any heat exchanger usually it comes between 0.45 to 0.8, usually most commonly 0.6 to 0.75 you will get most commonly. This is the range usually, but most commonly you would see 0.65, 0.7, 0.75 like that, very practically I am talking. Okay. Now we understood what is effectiveness. Second thing is the number of transfer units, NTU. NTU is defined as UA by m dot Cp small. But take care that U, whenever U is given in watt per meter square Kelvin, keep the always Cp in joule per kg. Take care of that. See, units. Cp should always be kept in joules. Many times kilojoules should be given. Convert into the joules there. Usually, practically NTU will be 1.15, 1.15 or 1.5 like that, 1.25 or 2.5 like that you will get somewhere in between 1 to 2 you will get 2.5 or 3. NTU will never be greater than 5 usually. 4 or 5 you will never see. You will always see around 1.15, 1.2, 1.25, 1.3 in that range, around that. NTU can be less than 1 also. NTU can be 1, NTU can be less than 1. But most of the occasions you see between 1 to 2 to 2.5 like that. There is a third dimensionless parameter. All are dimensionless parameter, capacity rate ratio. C is equal to, we have two capacity rates, m dot Cp small by m dot Cp big. We have two capacity rates, right? Smaller capacity rate, two fluids are there, hot side and cold side. Calculate the capacity rates. What is capacity rate? M dot Cp product. Smaller capacity rate by bigger capacity rate will give the capacity rate ratio. C is equal to 0 if m dot Cp big tends to infinity. That is when will it will happen? That is when one of the fluids is undergoing phase change. When one of the fluids is undergoing phase change, like steam condensation, or evaporation or boiling, anything, all are one fluid is undergoing condensation or boiling or evaporation. One fluid is undergoing phase change, then automatically C will be 0. So effectiveness will always be less than 1. NTU can be greater than 1 or can be less than 1 or can be equal to 1, but rarely it will cross 3 or 4. NTU will never be more than 3 or 4 practically. Very rare that is. C, the maximum limit of C will be equal to 1. When the capacity rates are equal, C will be 1. When C will be 0, if a denominator is infinity, that is when one of the fluids is undergoing phase change. A fluid undergoing phase change will have infinite heat capacity rate. If one fluid is undergoing phase change, for that heat exchanger, C automatically becomes 0. Best example is steam condensation, steam condenser. Okay, we have defined 3 dimensionless terms, effectiveness, NTU and C. For any heat exchanger, effectiveness is a function of NTU comma C, any heat exchanger. For parallel flow heat exchanger, I am giving the relation. For parallel flow heat exchanger, this is the relation for NTU. 1 minus e to the power of minus 1 plus c into NTU by 1 plus c. You have to mug up this formula. and for counterflow heat exchanger, you have to mug up this formula. Minus 1 minus C into NTU by 1 minus C into minus 1 minus C into NTU. This is for the counterflow. This is for parallel flow, this is for counterflow. And just like LMTD has, I have given you two special cases regarding LMTD, I guess. I remember just now some time ago, I had given the two special cases of the LMTD of the heat exchanger. One case is one fluid is undergoing phase change. I said that LMTD is same in both parallel flow and counterflow, particularly when the steam is condensing. Second case I have given regarding LMTD is when capacity rates are equal. When capacity rates are equal, what would happen for the counterflow, which is called as the balanced counterflow, that also I had given. Now again I will give the two special cases regarding the effectiveness. Two special cases of heat exchanger regarding effectiveness. Case 1. When one of the fluids is undergoing phase change, like in steam condenser. Best example for the phase change is steam condenser. Then automatic, just now I said, then C value will be 0. Why C value will be 0? Because denominator of that C, C definition becomes infinity. When steam is condensing, its capacity rate will become infinite. So C automatically becomes 0. Then effectiveness of the parallel flow, if we just look at the previous formula, C I put 0 here, C I put 0 here. It becomes 1 minus e to the power of minus NTU. Look at this, 1 minus e to the power of minus NTU. And look at this counter there. It put C is equal to 0 here, C is equal to 0 here, C is equal to 0 here. It becomes 1 minus e to the power of minus NTU. All this will become 0, so you will get the same thing. And effectiveness of the counterflow also, you will get 1 minus e to the power of minus NTU. That means when one of the fluids is undergoing phase change, parallel flow and counterflow heat exchangers will have the same LMTD. Similar case we have seen there in the LMTD also. Parallel flow LMTD, counterflow LMTD is same. Parallel flow effectiveness, counterflow effectiveness is same. Areas will be same. It does not matter. It does not matter what type of heat exchanger you are designing. If one fluid is undergoing phase change means condensation, evaporation, boiling, it does not matter what kind of heat exchanger we are going to design. Parallel flow design, you will get the same area. Counterflow design, you get the same area, same LMTD, same effectiveness. It does not matter. So what kind of heat exchanger you are going to design finally. This is one case. Case 2. When both hot and cold fluids are having equal capacity rates, that is m dot h Cph is equal to m dot c Cpc, then what will the value of C then? C will become 1. Okay. Then what will happen to the effectiveness of the parallel flow? Look at this, 1 minus e to the power of minus 1 plus C into NTU by 1 plus C. It becomes 1 minus e to the power of minus 2 into NTU by 2. This is for the parallel flow. And effectiveness of the counterflow. What is the formula? 1 minus e to the power of minus 1 minus C into NTU by 1 minus C. C is 1. 1 minus C into u to the power of minus 1 minus C into NTU. Check this. It will become what? All this become 0. E to the power of 0 is 1. This numerator is 0. All this is 0. 1 into 1, 1. 1 minus 1, 0. Undefined. Similar thing we have seen in LMTD also. Counterflow, look at the second case of LMTD in the counterflow. We got the same ambiguity. Then what did you do? We have used the L'Hospital's rule. Then from L'Hospital's rule, effectiveness of the counterflow will be, this is a very important formula, remember. When C is equal to 1, effectiveness of the counterflow heat exchanger. What is that heat exchanger it is called? It is called as the balanced counterflow. This is called balanced counterflow. Why balanced? When do you say a heat exchanger is balanced? When the capacity rates are equal on hot side and cold side. That is the meaning of the balanced. Under that case, effectiveness of the heat exchanger is for counterflow case, NTU by 1 plus NTU. NTU by 1 plus NTU. Please remember this formula. So this is the problem on heat exchanger. In an open heart surgery under hypothermic conditions, patient blood is cooled before the surgery and rewarmed afterwards. It is proposed that a concentric tube, what is the meaning of this concentric tube? A tube in another tube. It is a problem of heat exchangers given in previous KTU paper. It is a concentric tube, tube in tube. This is of length 0.5 meters. Is to be used for this purpose. What for? Is cooled. It is cooled with a thin walled inner tube having a diameter of 55 meter, 55 mm. Very thin walled. This is a thin walled, therefore we are neglecting the conduction. If water at 60 degrees Celsius is used to blood entering at 18, okay. Water at 60 is used to blood entering at 18. What is it? Is a counterflow heat exchanger, right? Concentric tube counterflow. In any, remember, whether parallel flow or counterflow, always use the hot fluid from left to right side. I am using the hot water there. Is used for this purpose with a thin wall having a diameter. If the water is used to use, there is THI. This is THI is 60 degrees. TCI, this is the blood, is 18 degrees. Okay. Mass flow rate of the cold fluid is 0.05 kg per second. Blood entering the heat exchanger. And what is the mass flow rate of the hot fluid? 0.1 kg per second, right? Now these only two temperatures are given. Only two temperatures given. No third temperature. Only two temperatures are given means we have to use the effectiveness NTU method. Now we have to use effectiveness NTU method only. I will highlight this. What is the meaning of that effectiveness NTU method? Please note that whenever you are reading the heat exchanger problem, if you are reading 3 temperatures minimum, then only go to the LMTD. In any heat exchanger, only 2 temperatures are given like this, like in this problem. We cannot make use of the LMTD and we have to use the effectiveness NTU method. I did not give the steps there. Only LMTD method I had told you. Effectiveness NTU method has got entirely different purpose, not to design the area, rather to calculate both the exit temperatures. Supposing in any heat exchanger, only THI and TCI is given, area is given. If you want to calculate both the exits, THE and TCE, only effectiveness NTU method can solve such problem. I repeat, in any heat exchanger, only 2 inlets are given, THI given, TCI given. Both the exits are not there. Can you use the LMTD method? No, you cannot. You have to use only effectiveness NTU method, which I did not give the steps. What is the effect, how to solve it? I am going to give. Now, actually, effectiveness NTU method main purpose is to calculate both the exit temperatures for a given heat exchanger area. In effectiveness NTU method, area is given. In LMTD method, area is unknown. You have to calculate the area. Here, area could be, you have to carefully read the problem. Here, you can calculate the area. Pi d into L, it is a concentric heat exchanger. Pi d into diameter given, length is given, pi d L will give the area of the heat exchanger. Here, area is known, but only you have got the 2 temperatures. You have to get the other 2 temperatures by using the effectiveness NTU method. I will highlight this effectiveness NTU method tomorrow. Okay. We can easily identify whether heat exchanger problem can be solved with LMTD method or effectiveness NTU method. We can very easily decide. If you are reading 3 temperatures, straight go to the LMTD. If you are reading only 2 temperatures, come to the effectiveness NTU method. The highlights of that method I will give in the tomorrow's class. How to solve that effectiveness method. And you know the effectiveness definition, formulae, NTU formulae, CWER. How to make use of these 3 parameters, effectiveness, NTU, C. In that effectiveness NTU method, tomorrow I will highlight. Okay.